Are we on? Let me check if we're on. We're live. Du- 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 du. Okay, looks like we're good. Okay, so hopefully for those tuning in, you'll be looking to revise for paper 2, and therefore you sat paper 1 earlier, a few hours ago. Paper 1 earlier, and I hope that went okay. Um, so, uh, what is the aim for this stream? What is the aim? Well, to reiterate again, I'm not a student, by the way. I'm not a teacher. I'm in between of like a teacher, tutor, or whatever, and a student. So I'm just someone who's already done this before ages ago, so I'm a bit rusty, but I think I've still got it, which is why I'm here to help. But I'm not like a full-on tutor or teacher or anything. Just to clarify. So therefore, I haven't saw the paper. However, I have tried to look at what various people said online and gathered some of the ideas of the topics that did come up. Um, so obviously you can help me out here, correct me if I'm wrong, but from what I've heard, obviously there are 10 questions. This is Edexcel, by the way. There was a integrating factor differential equation, first order. There was a triangle question with complex numbers and geometry and stuff like that. Argand diagrams. Uh, Improper integration. Was that mixed with partial fractions as well? So you needed to like split a partial fraction like this. Say like in the form ax plus b over hang on, not like that, sorry. Ax plus b squared. No, my bad, sorry. 8x squared plus b. There we are. Into the form uh, of that, right? Uh, okay, so yeah, there was that. So partial fractions, improper integration. There was, I think, question 1, was it? The first one, that invert a 3 by 3 matrix and do some stuff with the determinant. Then there was a methods of differences, a volumes of revolution, and the second order differential equation. I think I'm missing something, but I think that's the gist of the paper, right? Again, correct me if I'm wrong. Um, but yeah, I think that's where we're at. So therefore, so what have I done today? What are we doing today? Well, in light of that, obviously now we have a much better idea about what paper 2 would look like. So it's kind of predicted the sort of questions that have come up, so the topics that have come up. So, is my pen working? So these are the predicted topics that, and I will always say you must revise everything, even in paper 1. You never know, they might repeat a topic for some random reason. Uh, but if you want to, if you want to see where you put most of your attention and what might help you the most, I would strongly in the next few days before Thursday look at these topics. Uh, so I've got down roots of polynomials. I have got an Argand diagram question. And now I am, I think, aware there was one that already came up, but I think that was more or less to do with plotting a complex number and then making a triangle. Was it? It's not like so I'm more or less referencing loci. So that's stuff like your stuff that looks like this. Okay, so your perpendicular bisector, your circle, or your half line. Okay, or mixture, and we'll be looking at some of that later. So that's more or less what I'm referencing here. Loci rather than just plotting stuff on an Argand diagram. But I reckon there'd be one there. Another one be series, and in particularly using standard results. So that is your year one AS version. That looks like R. That uses R squared, and R cubed. Okay. And so I'm aware there's a method of differences, but there should be probably another series question related to this. Okay. Maclaurin. So there'd be a little question on Maclaurin, I reckon. Maclaurin series. Five. Proof by induction, because that didn't come up. Uh, Six. Vectors, which will absolutely 1,000,000% come up. Absolutely. Because it didn't come up on this paper, did it? Absolutely will come up on this one. Question 7. Couple. Okay, so actually no, I'm gonna say this first. Transformations. No, linear transformation, I'll probably say. So I'm aware there was a little matrix question. To do with but it was like a little one trying to invert it and then find the determinant. But again, correct me if I'm wrong, but I don't believe there was anything particular to do with linear transformations. So that's stuff like knowing your rotation matrices, your reflections, and including invariant lines and points, which I think may come up. And then point A I put was uh, coupled first order differential equations. So that's when you have two systems of differential equations and you have to sub one into the other and then stuff like that. DEs, okay. So again, I'm aware that there were already two differential equations. First order of integrate factor and second order. I'm not sure if it's homogeneous or not. However, I think there will be another one coupled first order, or perhaps potentially uh, something to do with like harmonic motion. You know that stuff in chapter, the final chapter with modelling. But I think this is strongly likely out of anything. They will absolutely ask you another differential equation question. I've noticed like 3 every year. Just because there's 2 on this one, do not rule it out. Okay. And I think they love asking duck coupled. Pretty much every year as well, from what I've noticed. It's a good way for them to fill up the marks in the paper. So yeah, they tend to ask that. Oh, 9, polar, of course. Polar. So that uh, so that's most likely integration, right? Area under a polar curve. But it could also be something to do with tangents, uh, tangents with regards to the initial line. So tangents parallel or perpendicular to initial line. And yeah, I guess as a 10th one, obviously at this point we've pretty much filled up a paper worth of topics really. You can get 75 marks worth of questions out of this. But these are the strong topics I predict, and I think you'll be in very good standing if you look at these. But I will always say, do not leave anything unturned, even what come up in this paper. But that's where most of your attention should be now for Thursday. And then the 10th one as a potential final, matrix modeling. So again, matrices came up. So either matrix mod. So I'm going to give a few possible topics here. So matrix modeling or systems of equations in some way, which can link to vectors. So determining perhaps if there is a line. So when they form a sheaf, perhaps the planes. You can then form a vector equation of the line, which then links to vectors. And then anyway, system of equations, or I'm gonna leave it there, but as a throwaway, I might perhaps say maybe even hyperbolic integration. Now, I'm a bit, I don't, again, I'm not sure. Did hyperbolics come up in the paper? I don't know. I think it did as a small question. I'm not entirely sure. I didn't see the paper, but and also I know there's quite a lot of integration already, but I think it's a way, but they do like to tend to ask it now and again to how to integrate a hyperbolic or use a hyperbolic substitution to integrate something. And I do have a question on that at the very end, a very nasty one that maybe we look forward to doing at the if we have time. But those are my predictions. And what I'm going to do actually, because again I need to go in a little bit, just for a little bit. Uh, if you want to look at the topics, how there we are. If you want to do anything with that or screenshot or whatever, I want to take a note. Those are my predictions. In particular, look at 1 to 9. Okay, 10 is they could ask it, but those are the 10 top topics I'd look at. Okay, but also if you have any questions or whatever, try and ask. And then when I get back, I'll try and look into it. But I'll be back in a few, and then we'll look at some questions. Okay, I am back. Okay, cool. Just checking my stream. Still good. Okay. Um. Okay, so those are the predicted topics. So what I did today was curate some questions from past papers, various past papers, related to these topics. So essentially, it should, in theory, look relatively similar to the questions on Thursday, the next paper, which are here. Okay. Okay, so this is the first question. So we are given a 2 by 2 matrix M with a constant K, and given that M squared plus 11M is AI, determine the value of A and show that K is this. Okay. So they might throw in a bit of matrix algebra. But it shouldn't be too bad, right? So, what do we have here? Question 1. So what's the matrix we're given? We are given M is minus 256K. And we are given, what was it, M squared plus 11M equals AI. Is that all right? Minus 256. Okay. Got that wrong then. Couldn't even copy the question right. Okay, so that should be right. Okay. So essentially, to find A and K, well, let's just substitute M into here. So M squared plus 11M is AI. Now, I remember is the square matrix, the identity matrix, right? So because it's a 2 by 2, we're going to need a 2 by 2 here. So 1, 1, 0, 0. Okay, so it's 1 on the diagonal and 0 everywhere else. And I'm not going to go to, I'm not going to waffle too much perhaps into why that is. But essentially, it's due to the fact if you times 1001 by any point xy, you will always get back xy because of how matrix multiplication works. So the idea is it preserves every single value, so it keeps it the same. I is essentially 1 in the matrix world. But anyway, so that's I. You should remember that hopefully. So yeah, we just need to substitute everything in. Well, we're going to need M squared, aren't we? So M squared, first of all, is minus 256K times by itself. And then we just need to compute the products. Okay. Again, so for the first bit, we're going to do minus 2 times minus 2, which is 4. And then 4 at 5 times 6 is 30. Then you do 30 as 4, which is 34. Okay, now for the second one, minus 2 times 5, which is minus 10. Minus 10, and then 5 times k, which is 5k. So it's going to be 5k minus 10. I'm going to write that here actually at 34, 5k minus 10. And then we're going to do this bit then to get this one. 6 times minus 2 is minus 12. K times 6 6k, so it's going to be 6k minus 12. And then for the last one, you're going to do 6 times 5, which is 30. And then k times k is k squared. So 30 add k squared. Okay, there we are. And now we just substitute it all into here. So this equation 34, 5k minus 10, 6k minus 12, and 30 plus k squared, plus 11m. So that's going to be 11 times this. So minus 22, 5 times 11, 55, 666, 11k is going to be AI. So A times I, that's just going to be A00A. Okay. So hopefully that bit's clear. And essentially now all we need to do is compare, right? Compare the matrix we have. Well, if we add, let's add this first of all. So 34 minus 22, add it entry by entry. So the 1 by 1 entry, row 1, column 1, has to add by the corresponding entry. So 34 minus 22, that is going to be 12, right? And then 5k minus 10, add 55. That's going to be 5k, add 45. And then 6k minus 12, add 66. That's going to be 6k, add 54, right? 54, not 45. Just to double check my answer. Cool. And then 30 plus k squared, add 11k. Okay. So that's going to be the k squared, add 11k, add 30. And that's going to be equal to this A00A. Okay, now we just compare. So we have 12 is A, which is great. And then 5k add 45 is 0, which means k is minus 45 over 5, which is minus 9. And it shows us k is minus 9, so we must have done it right. Cool. Okay, that's part A. So let's have a look at part B. Okay, so part B says determine the equations of the invariant lines of the transformation represented by M. Okay, so this is what I picked this question sort of deliberately. And for this particular reason, I want to go over a question like this. Uh, so, okay, actually, I wrote some of it here, actually. So, invariant lines, invariant lines, invariant lines. Okay, the last time I checked the textbook doesn't actually go into this at all. However, they still examine you on it, so it's not the best, really, is it, from Edexcel? But I'm going to go over how you tackle these sort of questions. So, they can ask you to find equations of invariant lines or invariant points. And we're going to go over actually both of them here in this question. So part B is asking us for the invariant lines by transformation. So it's quite typical, but a typical question. However, it might be bit new because the text it's not covered very well. But hopefully I can go over it now. Okay, so let's jump into it. So um, actually I'll do it here actually. So invariant lines. So a variant line, essentially, when we talk about invariance with the transformation, it's something that stays the same after the transformation. So say if we have a point here, and then we apply transformation to the point. So say we have the transformation m times by our point xy. Then we get another point, okay? So we get another point like AB. And that's the whole idea of transformations, right? A linear transformation, we map one point to them to another, okay? Uh, so invariance then is the case where it remains the same. And so there are two things we want to look at: invariant lines and invariant points. Now, invariant points will stay the same. So if we have a transformation m here at x of y, it will remain x and y. Okay, and then there's some stuff we can do with that. But there's also invariant lines. So a invariant line is again kind of what you think. So I have a line here. Uh, when we apply transformation to the line, so every point on the line, this line will stay exactly the same, right? The same gradient and the same y-intercept. Okay. Invariant line. And that's the key property, right? However, that does not mean every point on the line stays the same. Yes, the line stays the same and the points are all still intact, but the points themselves do not have to remain where they are. They can still move up and down the line as long as they're still on the line will stay the same, okay? So say if we applied the transformation and this point here moved to here, still on the line, and every other point worked the same way. So then say this point moved to here, and then this point moved to here, and then all the points move around, right? So the points are not invariant because they all move, they change. But because they all move and they're still on the line is invariant. However, the points themselves are not invariant. So that's the key distinction there. Okay. Invariant line does not mean the points are also invariant. The points can move as long as they move on the line. Okay. But what that does mean is because it's the same line, when you apply the transformation, it will still have the same gradient and the y-intercept because that's what defines the line, right? So that's the key thing we're going to work with here. So how do we apply transformation then? Well, M, which is our transformation, because we want to work out the invariant lines under M. So M's our transformation. So the transformation times by our point equals another point. Okay, so say the line before is y is mx plus c. Okay, so that's a line before a line before we apply the transformation. So any generic equation of a line would be x, which is so xy would be x mx plus c. Okay, hopefully you can see that. So that's just x, the point, and then y is mx plus c. That's the general coordinate of a point, general coordinate of a line, right? So as a coordinate, it'd be x mx plus c. Now, in order for the line to be invariant, so the line has to stay the same, it has to have the same gradient of y-intercept. So M and C have to be the same. Uh, but the point doesn't. So that means x can change, uh, which we'll denote with x dash. Okay. So the point x can change, but the gradient has to stay the same. So this will be m x dash plus c. Okay. And that's the key point now of invariant lines. It will always work like this to compute an invariant line of a transformation. So hopefully you get that. That's the key critical point here, essentially. Is to notice, well, the point doesn't change, so it'd be another x coordinate, x dash, but because it's the same line, the gradient m and c, the intercept, has to be the same. So we keep m the same, c the same, but x can vary because it's a different point. Okay, so that's the key idea. So essentially then, what we're going to do is to find the invariant line, is to try and work out, try and explore this, create equations from this, and determine values of m and c to make this happen. So let's just do that then. So this is the general procedure. So m, if we remember, is -2, 5, 6, and k, which is -9, times by this point, this general point on the line, mx plus c, which represents the line. This is the transformed point, so x dash and mx plus c dash. So the point can move on the line, but the line has to be the same, which is reflected by keeping m and c the same, but we change that x coordinate, okay? So hopefully I'm drilling clearly here that the points that change, but they only move on the line because the line is invariant, it stays the same. Okay, so now let's just times this at create equations then. So therefore, if we did work this out, -2x plus 5 mx plus 5c, times 5 by this, that will be x dash, and 6x minus 9 mx minus 9c would be x dash plus c. Okay, well, we can actually get rid of x dash here. We can substitute x dash into the second equation. So therefore, we're going to get 6x minus 9mx minus 9c is going to be m times this top one, so it's going to be minus 2mx plus 5m squared x plus 5mc plus c. Okay, so times substitute x dash the first equation into the second. So m times x dash times everything here by m, and then add the c. So hopefully you can see what I've done there. And yeah, so I think the good idea is to group x terms together and keep everything on the other side, perhaps. So let's do that then. So x lots of 6 minus 9m plus 2m minus 5m squared. Okay, and that's equal to 9c. Move all the constants on the other side. So 9c plus c plus 5mc. Okay. We can do some simplifying here. So that's going to be x of 6. So it's going to be minus 5m squared minus 7m plus 6 is equal to 10c and 5mc. So there's not more else we can do here. Okay. Right. So every invariant line has to satisfy this. But because x changes here, we don't really want to solve for x, weirdly enough. We don't care what x does. Um, okay, so what we should do here is, I think, is actually say this. X of minus 5m squared minus 7m plus 6 minus 5mc, so move it on this side, minus 10c is 0. And you can kind of potentially maybe see that this is in the form of a mx plus c, different c's and m's here. Okay, so this is 0. So how do we get 0? Well, a line has to be 0. So this big M plus C. So I'm going to be clear. This is now big M. And this is going to be big C. And so this line here, big M of X that we formed plus C equals 0. Okay. So C is this bit and M is here. Okay, so how does this equal 0? And so we can't set X to be 0. Because X will vary. X is not invariant. We only want invariant lines here, not invariant points. So X, we can't do anything with X here. X will vary. We can't do anything about that. So how do we ensure? Well, to make sure this is 0, well, M's gonna have to be 0, isn't it? To make sure that for any value of X, this part will always be 0. So therefore, you're going to left with C equals 0 as well. So in order for this to be 0, this whole equation, this part and this part both have to be 0, okay? Because X can't, you can't just force X to be 0 here, because X will vary. So to make sure it becomes 0, the code M has to be 0, okay? This factor of X here. So hopefully that is clear. So that means that, well, M is this, so that means we get two different equations. So 5 minus 5m squared minus 7m plus 6 is 0. Now we can solve this quite nicely. You can solve this in the, I don't know, well, you can, the way I like to do it to make sure if you're a bit worried about using the calculator, maybe not showing you working, just jot down very quickly the quadratic formula. So that'd be 7 plus, minus 7 plus or minus minus 7 squared b squared minus 4 ac all over 2 of minus 5. And then you can just bung that into the calculator. Well, don't put this in the calculator, but use a quadratic solver. So you make sure you definitely don't make any errors. So it takes a few seconds to write down, but you can be sure you've done your work. So now, if we solve this quadratic, you should get minus 5, minus 7, 6. Well, M is either 3 over 5 or minus 2. Okay. And now we look at C. So now this part has to be 0 as well. Because obviously what's happening here as well is 0 minus 0 gets us 0. So that's why that's how we can solve this equation without having to worry about X here. Okay. So let's look at C. So that means minus 5mc minus 10c is 0. So that's the C part. So C 0 as well. Well, I guess we already have M, don't we? So let's have a look for C. So C uh, would be, let's factorize. So C of minus 5m minus 10 equals 0. Um, well, that either C is 0 then, or M, or 5m plus 10, 5m equals 10 minus 10. So M would be minus a half, right? No, minus 2. Sorry. Okay, because obviously we can set this bracket to 0, this factorization. Okay, so we've got some possibilities here. So, um, So now we just have to look at all the solutions we have. So, bear in mind, both of these have to happen, by the way. First of all, let's look at the solution for part one. We're also going to need to take one of these solutions for here. Both of these have to be zero, so we're going to take one solution from each possibility scenario, right? So I guess case one, if you wish, from here m can be 3/5. But then it says C0 m is -2. Well, m is not -2 yet, so the only thing we can accept here is C0. And obviously, therefore, the equation would be for y is 3/5x plus 0. So that's the invariant line here. And the second case is when m is -2. But actually, we've got some possibilities here because m -2 sets this to be 0 as well. Or C is 0. But m -2 is the only solution we need here. So y -2x. And actually, because it doesn't matter what C we pick, actually. Um, as long as m is -2, it makes both parts 0. And if we pick C0, it's a bit redundant, really, because m can be -2 and that still make it 0. So C0 is just actually one solution here. So we can just put m is -2. So that is actually the invariant line in this case. So these are the two invariant lines. And let's just write that down here. 3/5x, y is -2x plus c for any c. Okay, for any value of c. Okay, so that's how the process goes for tackling these invariant line questions if they ever come. I think it has a good chance of coming up if I'm honest. Some sort of business with invariants. But this is the process, right? As long as you note um, that you have to keep the gradient m the same and the intercepts m and c remain the same, and you formulate it like this: so x dash mx dash plus c. When you equate them, then you can get you do some simultaneous equations. That shouldn't be too difficult, hopefully. And then you get to this point, and then you have to set both of them to 0. Make sure x cannot be 0, so you need to make sure both parts of these are 0. Okay. And I guess, yeah. And also, by the way, don't rearrange this for x either. I know some people might be tempted. So x would be what? 10c plus 5mc divided by -5m squared minus. Don't do that because again, x can vary. So we don't want to fix x here. So this is the only way we can kind of solve the equation, right? So I'm splitting this up and realizing, I guess perhaps it's the line if you wish. So in order for this to be forced to 0, m has to be 0, and then therefore c 0 as well. Okay, so both parts have to be 0. Okay. Okay, so hopefully that's clear, and everything should follow from that, right? Hopefully it's not too complicated, but that's the process. Okay. So then you're gonna have two cases. Then you have two cases. Obviously, set m is 0. So what do you get here? And then when the second part is 0, and then kind of work with the cases you've got. But hopefully it's not. That's the process, right? It's pretty much the same sort of thing. Cool. So part C then. So that's all about invariant lines. Then it says state which if any of the lines consist of fixed points. Okay, so which line? So now this is starting to go about the fixed point business. So now it's asking for which of the fixed lines, there's only two of them obviously, when the points on the lines also remain in the same place, all of them on the line. So in order to deal with that, we need to look at what an invariant point looks like. Okay, so we're going to need to look at invariant points, not lines this time. And this is actually a lot nicer. Um, so invariant points are x, y remain exactly to x, y, right? No x dash, y dash, because the points remain the same as well. Okay, so that means, well, as a result, m uh, of xy has to equal xy now. Not x dash, not mx dash plus c, what xy, okay? And actually, there's not a lot of stuff you need to do here. I know it's only one mark, but actually it's quite simple. Because look what happens here. So let's substitute m in again. So m was minus 256k. Okay. 6 and k, oh, 6, and k is minus 9. Times that by any given point xy, and we want to fix it so it remains the same. So xy. And then let's have, again, exactly the same process. Form equations and see what happens. So that's going to be minus 2x plus 5y is going to be x. And 6x minus 9y is going to be y. And yes, solve these similar equations. Um, well, the first one, if you have a look, it's going to be 3x is 5y, which then means y is 3 of 5x, which is a line. So it's telling us on this line, every single point is invariant, right? Because the invariant point has to satisfy this condition here. And that's what's happened. And the second one, well, again, if we 10y, if we add 9y, it's going to be 6x, which actually then means what y is 6 over 10x. 6 over 10 is 3 over 5. So it's the same point again. So this has to be the only line. This is the only way of choosing points that are invariant. So we pick an x coordinate and y has to be 3/5 of that. So in other words, the line 3/5 x ensures that every point is invariant. Now let's compare. Do any of these lines match this? Let's look at our answer. Yes, it does. The first one, 3/5x. But it can't be this one minus 2 because that's a different gradient. That it won't ensure all the points are invariant. But this does, it's matched. So actually our answer is yes. So the line or we can say the invariant line or the line y is 3/5 x does consist of invariant points. But I guess be clear as well, but not the line y is minus 2x plus c. So yeah, so I think that's question. I think that question is really good for demonstrating invariant lines and invariant points. So hopefully that is clear. I think it is quite important to understand this sort of thing because I think it could come up, and if it does, there's not a lot of resources for it. The textbook's quite shocking for it. So yeah, that's why I'm going with it. Now, hopefully it's kind of clear. That's the process you want to go through. That's how it. That's how that works. So cool. So that's question one done. Let's have a look at question two. Here we are. And it's just a nice little Maclaurin series, right? You're going to get a question like this very, very likely in your paper on Thursday. Just a little Maclaurin series questions. They all look kind of similar, really. Derive the Maclaurin series for a particular function and then perhaps do some with the function. And that's what's going on here. So we need to work out the Maclaurin series of arc sine of x. We need the first two non-zero terms. Okay. So actually, it's in the formula book that if I can find it, here we are. The series. This is the Maclaurin series, the first one, and we need to do so the Maclaurin series, a general Maclaurin series, is f of x is equal to f dash of 0 plus x f dash of 0 plus I believe it's f. No, f dash dash of 0. No, so that's f of 0. Sorry. I need to look at it again. Plus x of f dash of 0 plus f dash dash of 0 over 2 factorial x squared, and then it goes on in the same sort of process. Okay, have I copied that down right? Let me just double check that. XF a dash, yep, lovely jubbly. Okay, and that's what we're going to do. So we know that y is arc sine x, we were given that. So really, if we are going to look with these Maclaurin series questions, if it asks you to essentially derive it, you're going to need to differentiate. That's make the bulk of it, right? And then you sub in f of 0 into each of them and see what happens. Okay, so that's what we're going to do. Now, actually, the first derivative is... Well, actually, first of all, let's know what f0 is, actually. So we want the first two non-zero terms. Okay, just to reiterate. So let's check. So f of 0 then, so arc sine of 0, so inverse sine of 0 is 0. So that's a 0 term. We're going to need to look for more. So that means f dash of x then, we need to compute it. Well, actually, the derivative of arc sine is very kindly, once again, I believe, written in the formula book. And it's here, the first one. Up here. 1 over root 1 minus x squared. Okay. And so therefore f dash of 0 is going to be substitute 0 into there. So what do you get? 1 over root 1 minus 0. You get 1, so that is non-zero. So I've got our first term, okay. Now we need to compute the second derivative. Before we do that, let's write this as a nice form to differentiate. This is basically now just normal maths differentiation. So that's going to be 1 minus x squared. We can say that's a minus a half, okay. And then we can use this, differentiate this via the chain rule. What's that going to be then? So times minus half times the power by the derivative inside. So that's going to be minus 2x of 1 minus x squared of minus 3 over 2. Knock 1 off the power. Okay. Doesn't look the nicest, does it? Well, this will simplify to x. So minus a half will cancel with minus 2. So x of 1 minus x squared to minus 3 over 2. Doesn't look the nicest, but let's see. What is f dash dash of 0? Well, it's going to be 0, isn't it, unfortunately? 0 times 1 minus 0 to the power of minus 3 over 2 will get you 0. So we're going to need to differentiate this monstrosity again. So again, now this is going to be a mixture of the chain rule and the product rule. So the triple derivative, the third derivative. So the product rule. So firstly, differentiate x and then leave this intact. So it's just going to be simply 1 minus x squared minus 3 over 2 plus x. And now we leave the x and then differentiate the second function. And it's the same sort of process. So it's going to be minus 3 over 2 times by the derivative, which is minus 2x inside the bracket. And then the same thing again, 1 minus x squared to the minus 5 over 2. Okay. And that's going to be 1 minus x squared minus 3 over 2. And hopefully this is non-zero. Minus, well, that's going to cancel to minus 3, isn't it? Plus 3x squared. 1 minus x squared to the minus 5 over 2. Okay, what does that get us? So let's substitute f dash dash. Let's substitute 0 into this. So that's going to be 1 minus 0 minus 3 over 2 plus, well, this is going to go to 0, right? Be times by 0. I don't need to plug that in. And actually, this gets us 1. And therefore, if we substitute this then into our Taylor series, f of x is going to be now f of 0, which is 0, x of f dash of 0, which is 1 here. So it's going to be x. And then f dash dash of 0 was 0. Then the third one will be f. If we add, it's going to be f dash 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 of x of 0, sorry, over 3 factorial x cubed. Well, that f dash dash of 0 is 1. We've worked out over 3 x cubed over 3 that's going to be 6. So it's going to be plus x cubed over 6, right? Great. Okay. Let me just check once more. Cool. Okay. So that should be the answer then. But that's the Maclaurin series of arc sin x, the first two non-zero terms. Okay. So that's part A. Then part B is, have a look. Then it says substitute x is a half into the answer to find an approximate value for pi. Give the answer in the form P over Q. Okay. So it's kind of like binomial expansion, right, in normal maths. Substitute a value into find an approximation. Well, I should probably say f of x is approximate to here. Okay. Yeah. Okay. But f of arc, so this is saying f of x, which is arc sin x, is approximate to x plus x cubed over 6. So then it said sub x is a half in, and we're going to need to sub it into both sides. So arc sine of a half is going to be approximate to a half plus a half cubed over 6. Okay, but what's arc sine a half? It's pi over 6. Well, that's great news, because we can just times by 6, can't we? So pi over 6 is, and let's compute this fraction. A half plus then a half cubed over 6 is 25 over 48 if we do this in the calculator. Therefore, pi is therefore going to be 6 times this, okay? And that is 25 over 8. And that is your fraction. Cool, in simplified form. Nice 2 marks. That is, there we go, lovely jubbly. P and Q, where they're integers. Perfect. Actually, what I do want to do quickly, just to demonstrate as well, I want to do a little cheeky part C. And what I want to do to extend this is I want to ask about the mean value. So I'm going to say, given that the integral of arc sin x dx is, I'm going to put this into an integral calculator actually. I did test it out earlier actually. Arc sin x, the integral is x arc sin x plus root 1 minus x squared plus c. I'm not going to give the plus c here because it won't matter because it will be a definite integration. But I guess, but yeah. That's the antiderivative. But given this, and you can check this is true if you differentiate, if you want to try that out. So given the integral arc sine is this, x arc sine x plus root 1 minus x squared, I want to find the mean value. So this is, I guess, a part C. Find the mean value of f of x. Okay, well, we're actually given an interval, aren't we? X is between -1 and 1. So therefore, the mean is going to be 1 over b minus a. Now, it's 1 minus minus 1, because x is between -1, x 1. So b is 1, a is -1. So that's where that comes from. Between b and a, which is between 1 and -1, of arc sine x dx. Now, actually, we're already given what this derivative is. So it's going to be, the mean is going to be 1 over 2, a half, of x arc sine x minus the root of 1 minus x squared between 1 and -1. Okay. Oh, plus, sorry. Plus, not minus. There we go. So that's the mean value. So we just need to substitute this in. Which is a half of one arc sine, so arc sine of 1, plus the root of 1 minus x squared. That'll be 1 minus 1, which should be root 0, minus 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 arc sine arc sine of -1, my plus the root of 0, right? Because root 1 minus x squared, 1 minus 1, gets you 0. Okay. So that's just plugging in the upper lower limits of integration here. And obviously subtract the upper by the lower. That's what I've done here. So that's going to be half arc sine of 1 is actually quite nice. Arc sine of 1 is pi over 2. So pi over 2 plus 0, that's pi over 2. Minus arc sine of minus, well, minus, that's going to be plus arc sine of -1. That'd be minus pi over 2. And actually, this goes to 0. And actually, I guess as a brief commentary, well, look at the graph of minus arc of arc sine, right? Which kind of looks like that, right? But this is the x-axis here at 0. So if we integrate it between 1 here and -1, well, uh, well, it goes to minus pi over 2, doesn't it? I think. What's, remind me what the graph of arc sine is, right? Ah, no, it doesn't look like that. On my apologies. Um, it looks like the cubic graph, doesn't it? There we are. That's arc sine of x, where that's the x-axis. Cool. So when it's 1 and -1, obviously that's going to be pi over 2, and that's going to be minus pi over 2. Well, actually, it's symmetrical, right? So think about what the mean value is doing. The mean value is giving us, if we sum the function over an interval between -1 and 1, it's giving essentially the average value of the function. That's what the mean is, right? The mean average of, if you sum all the function values, what is the mean value? But actually, because we add in, and because it's symmetrical, here on the top and the bottom, you're kind of taking away all the positives by the negatives. Because it's between -1 and 1, it'll be the same underneath the graph as above the graph. So basically, the positives take away the negatives. Because of the symmetry, you get 0 as a result. Okay. So that's just a nice little extension question there. And the reason that's because I think the mean value will come up in paper 2 as well. So it's quite good for like even just a 2 marker to test your knowledge on it. Okay, that's a nice question. To question 3, I prove by induction. Okay, so we want to prove prove f of n, which is, remind me what that is. 3 of 2n plus 4 minus 2 to the 2n, was it? Was that the question? Minus 2 to the 2n is divisible by 5. Cool. So, hang on, was it 2n plus 4? Did I get that right? I need to make sure I copy it right, because I messed up there. Okay, that's great. So, again, typical with proof, I think a proof prediction would definitely be coming up. I think probably the most likely one, and probably the hardest one to do as well, is divisibility stuff. So I think it's best we practice a divisibility question. So yeah, let's do it. So hopefully you're familiar with the mechanism of proof by induction. We're going to need a basis step firstly. So that's the first value of n. Now if we have a look at the question, for all positive integers of n, so n is 1, 2, 3, 4, 5, 6, and so on. So the first number we're going to test is n is 1. So we're going to let n is 1. Therefore, f of 1, which is 3 to the 2 of 1 plus 4 minus 2 to the 2 to the 1, showing clearly we're substituting it in. That'd be 3 to the 6, wouldn't it? 2 plus 4, 6, minus 2 squared. That will be, if you put it in the calculator, 725, which is divisible by 5. I guess we want to be clear, you say as 725 over 5 is 145, which is an integer. Therefore, is true for n is 1. Or I should say, statement is true, more specifically. Cool. Now we need an assumption step. Assume n is let n assume statement is true for some integer n is k. Therefore, what this means is f of k, which is 3 to the 2, 2k plus 4 minus 2 to the 2k, is divisible by 5. Okay, so that's the assumption step. Now for the meaty bit, the inductive step. We're going to let n be k plus 1. Okay. Therefore, f of k plus 1 is going to be 3 to the 2 of k plus 1 plus 4 minus 2 to the 2k plus 1. Okay, and now we need, the aim is to show that this is divisible by 5. Now, there are various ways of tackling these sort of divisibility questions, but this is the way that will always work. And it's actually saying, and what you got to do is, what you want to do is uh, consider f of k plus 1 minus f of k. Um, and the idea is, since f of k is divisible by 5, this and if f of k plus 1 is divisible by 5, then this will also be divisible by 5, the whole expression here. So if we can show this is divisible by 5, then f of k is divisible by 5, then so will this. So what we're going to do, and this is the little trick, is to consider f of k plus 1 minus f of k. Okay, sometimes you can work directly and show it directly. F of k plus 1 is this, but this is the best way with all divisibility questions. Okay, if they ever do come up. Okay. So we need to show that this is a multiple of 5. That's what divisibility means, right? So this has to be multiple of 5 in order for it to be divisible by 5. Okay. Let's work this out then. So f of k plus 1 minus f of k is 3 to the 2k plus 1 plus 4 minus 2 to the 2k plus 1 minus f of k, which is going to be 3 minus 3 to k plus 4 minus 2 to the 2k. Right, yo. Um, okay, okay, so let's manipulate it. And actually what you will see eventually is actually this is going to be some lots of multiple f of k. And that makes sense because if f of k is a multiple of 5 and this sum or difference is a sum of 5, then therefore they're going to have to be multiples of each other. So that's the whole aim here, to show that this is a multiple of f of k. So we are going to have to rearrange this to make sure that this is in terms of f of k. That's the strategy behind this, okay? So hopefully it kind of makes sense there, but that's the strategy here. Um, so let's rearrange this. Let's do some stuff. So I think the best strategy is to expand the brackets to see clearly what we're working with here, and then group terms together. So this will be 3 of 2k plus 6, right? Minus 2 to the 2k plus 2 minus 3 to the 2k plus 4 minus 2 to the 2k. Uh, cool. Uh, and I think now what we should consider is let's group like terms together. So 3 to the 2k plus 6, I think we could get this in terms of 3 to the 2k plus 4. And so let's do some rough notes here. So 3 to the 2k plus 6. And so 3 to the 2k plus 4, if we remember our index laws, we're going to have to add 2. So we're going to add a power 2. We're going to need times it by 3 squared. Okay. So then 2 add 4 is 6, add 2k. So that gets our original result there. So index laws are going to be critical here. So 3 squared, uh, which is great. And then we want to look at the minus 2 to the 2k here. And then I think we could do the same sort of thing here. 2 squared, right? So, no, oh, my bad. Hang on. That's going to be 3 squared minus 1, isn't it? If we factorize it. Minus 2 to the 2k. That's going to be 2 squared minus 1. Isn't it? Plus 1, sorry. Plus 1. Hopefully you can see why this is true. Oh, hang on. some issues with a minus it. F of k plus 1, which is this, minus f of k. So that's going to be minus this add 2 to the k. Okay. So that's going to be 2 squared minus 1, right? Uh, yes, okay. So let's expand it. 3 to the 2k plus 4 times 3 squared. That'd be 3 to the 2k plus 6 minus 3 to the 2k plus 4. Yeah. Minus 2 to the 2k of 2 squared, which should be 2k plus 2 plus, and that should be plus, shouldn't it? Plus 2 to the 2k. Cool, so that should be okay. Now let's work what's inside the bracket. That's going to be 9 minus 1, 8. Minus 2 to the 2k. 2 squared minus 1, that's going to be 4 minus 1, 3. Uh, so that's going to be 8. So that's going to be 8 lots of 3 to the 2k plus 4. Minus 3 lots of 2 to the 2k. Okay, so notice this is vaguely similar now to f of k, right? So there's a 3 2k plus 4 with a multiple minus some lots of 2 to the 2k. We're nearly there. Okay. Uh, but where should we go from here? So we need this to be multiple 5, and we need this to be a multiple f of k, realistically, right? F of k of x. Okay, oh no, sorry, m lots of f of k. Okay. But this is another trick we can do. Well, can't we split this 8 up into 3 and 5? Can we not say this is 5 lots of 3 to the 2k plus 4 to match this? 5 lots of 3 to the 2k plus 4 plus 3 lots of 3 to the 2k plus 4 minus 3 lots of 2 to the 2k. In other words, 5 to the 3 2k plus 4 plus 3 lots of 3 to the 2k plus 4 minus 2 to the 2k. If we factorize it out, I think we've done it, because can't we now say this is equal to 5 lots of 3 to the 2k plus 4? And that's great. That's a multiple 5. So that's divisible by 5. But what about this? Is this divisible by 5? Well, it's a multiple 3. But then what is this? 3 to the 2k plus 4 minus 2 to the 2k is exactly f of x. So this is 3 f of k. F of x, 2 to the 2k, f of k. F of k dot f of x. Yeah, so this bracket here, inside here, is exactly f of k. So I think we've done it. So this, bear in mind then, f of k plus 1 minus f of k. That's the original. That's what we've done all the way through here. Well, that's going to be 5 lots of 3 to the 2k plus 4 minus 3 f of k. So therefore, we rearrange for f of k plus 1. That's going to be 5 lots of 3 to the 2k plus 4 minus 2 f of k. If we add f of k to both sides. We've done it. This has to be divisible by 5, because this is a multiple 5. and this is a multiple 5, and if you subtract multiples of 5 together, that still has to be a multiple of 5. So how do we write that? As 5 lots of 3 to the 2k plus 4 is divisible by 5, and 2f of k is divisible by 5, because obviously f of k is divisible by 5. Therefore, the difference is also divisible by 5. And there we have it. That's our proof done. So there we show that f of k plus 1 is also divisible by 5. This is a really nasty one. I just took a divisibility question, but that's really nasty in my opinion. Um, from 2019, the paper there. It really makes you. I think if you really want to test your knowledge on divisibility proofs, this is a really good question to try this out. Um, yeah, but yeah. So the key here is to do f of k plus 1 minus f of k, and try and get that into a multiple of 5. Okay. For some reason, it just tends to be nicer to work with than just considering f of k plus 1 directly and trying to like manipulate it in terms of powers. In terms of it's really hard to do, if not impossible. But this is the way to do it, okay? And the reason why it's hard as well is because if you just manipulate f of k plus 1 directly, you are not using your assumption. That is the key with these divisibility questions. You need to use your assumption here. Okay, so the way to force you to use your assumption is to write this directly minus f of k, and then it works from there. Okay, so you do this, and then you try and show that this is divisible by 5. And to do that, you're going to need to try and find a multiple f of k by factorizing and stuff like that, and bringing powers out. Okay. So that's a strategy of that. I guess to write the final conclusion then for the final mark. So therefore, statement is true. No, I should say f of n is divisible by 5 when n is 1, and is divisible by 5 for any given integer n is k plus 1, provided uh, it is divisible, if I come right, when n is k. Okay, so that's our assumption. We assume n is k, f of k is divisible, um, and then we show n is k plus 1 is divisible. Okay, therefore f of n is divisible by induction by 5 for any positive integer n. And I guess very quickly that's because, well, from the start, the basis n is 1 is divisible. And then we can kind of use the assumption. So say k is 1, then that means n is 2, k plus 1. Will be shown n is 2 then is divisible, the next number after 1. And then we can assume, well, f of n is k is 2. Well, we know k is 2 then is divisible. So then, by this logic again, the next number n is 2 plus 1 is 3. F of 3 is divisible, then therefore f of 4, the next number f of 4 is divisible, f of 5, and it goes on and on and on. So that's the idea behind that, and that's induction. Not the nicest one, I'll admit, but yeah, they could very easily come up. And that's how you tackle it. As long as you realise to consider f of k plus 1 minus f of k, and then do it from there, I think you'll make your life a lot easier. But yeah, there we are. Okay, let's have a look at this question, and it's a polar integration question. Okay. So again, something like this can come up. There's no polar question in the paper, so it's looking quite. Probably there will be a polar question in there, but there could be like a mean integration one, like this one. Okay. So we're given a sketch of two polar curves. I mean, essentially need to show the area is this. Okay. Well, again, with these area questions, I kind of like to work out where where we need to integrate to and what we're integrating. So I guess very rate. I'm going to write this here. Um, so the initial line. So obviously, remember how polar graphs work, polar curves. We start from the initial line, and then obviously that's when theta is 0, and that's the R value here of the two curves. And then obviously we move theta up. So then theta, we go around the initial line, 360 degrees. Um, and then that's how we get our graph. And then substitute it to get R, and there you are. Okay, so really the region starts at this intersection point P, doesn't it here? That's where the region starts to be shaded. And actually, then if you go beyond that, well, really, the area is essentially between when the angle theta is P and when theta, when between when angle is, uh, when the when we look at the angle bigger, when well, at P, okay, so at the intersection point, after when we go beyond this, clearly C1 uh overrides C2, right? If you look at here, the area, I guess, between the curve and the initial line, kind of like normal integration. C1 overlaps C2, right? In a way. So, really, if you can't, it's hard to explain this sort of visualization stuff, graphic stuff, but after P, C1 is kind of bigger than C2. C1 overlaps C2. So really, the area explicitly in this region, well, that's going to be the C1 minus C2, isn't it? The curve C1 minus C2. I guess to visualize this, let me try and also get see what I'm showing here. So that's C1 vaguely. This is O, and this is P. Okay. Uh, okay. Now after P, let's say if we just took the area of C1, that would be all this area, right? Well, no, actually, no, that's not right. So hang on, I'm not exactly right. Oh, I didn't want to delete all that. I'm trying to explain this visualization stuff as best as I can. So this is origin, so that's our initial line here. So then P is kind of up here, right? Now, actually, beyond P, we want the area underneath, between the curve here and the initial line. So it's going to look like this, isn't it? So that's the area if we just took C1. But then actually, we kind of want to get rid of this distance between, if you look here, P and the initial line. We want to get rid of this area here underneath this section here. Well, this section actually corresponds to, if you have a look here, this section here, that is C2. If you look here, this little bit over here, this region here is C2. Is overlapped by C2. So I think if we take away the overlapping area here with C2's area, I think we just get R. But hopefully that is clear. It's really quite hard to explain this, but hopefully that is somewhat clear. So that means the area, let's say, I think it's quite nice if we took this to pi over 2. So obviously this is when theta is pi over 2. Obviously that's perpendicular to the initial line. Uh, that's when it's symmetrical. So I think if we double the area between P, with theta is P and theta is pi over 2, between the area C1 and C2, d theta, I think this gives us the area of R. I think. Um, and I think that's all we need to do. Um, so yeah, so that's it. Yeah, so that's probably the hardest bit of this type of questions to work out how to define your area as an integral. But once you do that, it's really just a bit of algebra essentially. But yeah, if you know your stuff, you should don't be put off. But yeah, hopefully that makes some sort of sense. Why this is the area of R, right? So do C1 going, which is bigger than C2 after this intersection point, and the curve and the region is starting after the intersection point. So C1 has to be taken away by C2 to get rid of the overlapping area um, that you get from just integrating C1 to then just purely get R. Okay, hopefully that's clear. So really what we need to do is to find P. So where does this intersect what angle? And then integrate. Obviously it's not that's not the proper integral, because if you remember the integral in polar coordinates is this formula here. But I'm just giving a rough like sketch here. I'm just doing some rough work to show clearly what the area is. Okay, so we need to find P, and then I think we need to substitute this in for R squared. But anyway, let's do that then. So, what was it? Question 4, is it now we're on? We need to find intersection. So the intersection point. Well, to do that, uh, we just set the two curves equal to each other. Because we're given the two equations, R is this and R is that. So substitute R into each of them. R into here and into here. Cool. So that means therefore 1 plus sine theta is going to be equal to 3 lots of 1 minus sine theta. Cool. Let's expand this out. So 1 plus sine theta is 3 minus 3 sine theta. And then let's put sine theta on its own. So 4 sine theta is 2, therefore sine theta is a half. And actually, if you know exact values, theta would be pi over 6 or 30 degrees. Let me do a quick sketch here. That's 30, and then it would be 150, which should be 5 pi over 6. Pi minus pi over 6, right? Uh, I've got that right. Let me have a check. Yeah, half and half. So these are the two solutions, right? In between 0 and 360, when the polar coordinates are defined. But actually, let's have a look here. Um, obviously, so those two angles correspond to the 2 points where they intersect. But the curve intersects here first, and then it intersects here next. But obviously, if you know, 30 pi over 6 is 30, so that actually means this has to be 30, right? So this is 30 degrees, or obviously pi over 6, which is the angle here, the theta, where they do two curves intersect. They also intersect here at 5 pi over 6, which we've worked out. Um, Uh, but we're not interested here. We're interested between P here, the first intersection, and pi over 2. Okay. But yeah, so we take the solution, pi over 6. Cool. And now we found the theta value. Uh, so that means the area then, right, it's going to be a half the integral between pi over 2 and pi over 6 now. But remember, this is two lots of it, okay? Because it's symmetrical. Let's explain that again. So between pi over 6 here and pi over 2, that's a half of the region because it's symmetrical at pi over 2, right? The middle line here. So if we double the area, we get this left side as well. So doubling the area we get here will get us the whole region R. Okay, so that's why we're doubling. And then it's going to be half of R squared d theta. But obviously we're taking away C1 minus C2, aren't we? So we're going to be taking on C1 squared minus C2 squared d theta. So that's going to be pi over 2, pi over 2, pi over 6. And now we substitute C1 and C2 in and square them. Okay. So it's going to be 1 plus sine theta squared. Take away C2, which is 3. Well, it's going to be squared. This is 9 of 1 minus sine theta squared d theta. And essentially, now it just boils down to working out this integral, which is normal math stuff at this point. That should be cool, I think. Cool. And yeah, let's work that out. So let's expand it. I think that's a good idea. So the integral of pi over 2 to pi over 6 of, well, 1 plus 2 sine theta plus sine squared theta minus 9 lots of 1 plus 1 minus 2 sine theta plus sine squared d theta. Okay, now let's simplify it. Okay, so 1, let's get the constants together. So 1 minus 9, that'd be minus 8. 2 sine theta plus 18 would be 20 sine theta. And then minus 9 sine squared theta plus sine, that'd be minus 8 sine squared theta d theta. Now we just integrate this. Okay. Well, we know how to integrate a constant and sine theta because that would be minus 8 theta and that would be minus 20 cos theta. The integral sine theta, remember, is minus cos theta. But sine squared is a bit weird. But actually, you should know the trick for this. You should know that cos 2 theta is cos squared theta. And then we can use the Pythagorean identity. So it's going to be 1 minus sine squared theta minus sine squared theta, which therefore means 2 sine squared theta is identical to cos 2 theta minus 1. No, 1 minus, no, we flip the negatives, don't we? 1 minus cos 2 theta. Therefore, and yeah, so now we've got an expression for sine 2 theta in terms of linear angles, right? So there's no squares, right? Well, cos 2 theta will integrate to sine 2 theta, a half sine 2 theta, sorry. And yeah, let's do that. So the integral then becomes, or the area is again between pi over 2. Let's substitute this in. And pi over 6 of minus 8 plus 20 sine theta minus 8 lots of this. So that's going to be minus, times this by minus 4 plus 4 cos 2 theta. And we can integrate all of these terms nicely now. So that will become minus 8 theta, minus 20 cos theta, minus 4 theta, and then plus 4, because cos 2 theta will integrate to a half sine 2 theta, so there's no negatives, and we halve the angle, because it's the opposite differentiation where we times it. Okay, and then so a half of, so cos 2 theta integrates, so that's a 4 lots of that would be 2 sine 2 theta between pi over 2 and pi over 6. So therefore, we just need to substitute that in. So we can actually bring the 8 theta and the 4 theta together. So that'd be minus 12 theta, which would be pi over 2, minus 20 cos pi over 2, minus plus then 2 sine of 2 pi over 2, which would be pi. And that, oh, and then we minus the lower limit, which should be minus of minus 12 of pi over 6, minus 20 cos theta, which should be pi over 6, and then plus 2 sine pi over 3. And then you just bung that into your calculator, okay? So the first bit would be minus 4 pi. And then let's work out everything else. Minus 20. Okay. And then apparently that's plus 11 root 3. Let's put that in right. Minus 20 cos pi 2 plus 2 sine pi. No, hang on. We didn't put the negative at the end. Hang on. No, that'd be 9 root 3. Okay, so that should be right. In other words, it'd be 9 root 3 minus 4 pi. Let's double check this is the right. This is positive, right? We can double check our answer by doing that. Oh, hang on. 9 root 3 minus 4 pi. Yeah, you get 3.022 something. That seems fairly reasonable. What does the answer say? It said it in a particular form, didn't it? What's the form? P root 3 minus Q pi. Yeah, so that's be right, surely. So P is 9, Q is 4, right? P root 3 minus Q pi. There you are, so that's your answer. Units, whatever, right? You don't have to put that at the end, but that's the area of R. Cool, lovely jubbly. Now we're going to move on to the next question. Question 5, is it now? So that's how you deal with an integral question like that. But yeah. So yeah, normally strategy is to find any intersection points and then take one curve away from the other. That's usually what it boils down to. Usually. But yeah, there we are. Now we got an Argand question. This is one that I think will probably come up. Like I said, I think there was an Argand one, but it was fairly tame. I think you're just plotting points on it and then drawing a triangle, something like that. But this will be like a proper one, like a locus one. So let's have a read. So in the Argand diagram, the points A and B are represented by the complex numbers, this and this, and they are endpoints of a diameter of a circle. Find the equation of C given it in this form. Well, this is the equation of the circle and complex numbers, right? So A is the center, B is the radius. Okay. But yeah, okay. Let's plot this first to see what we did. So this is the real axis, imaginary. Um. So A is minus 3 plus 2i. So that's be minus 3, 2i. That would be A, and then B would be 5 minus 4i. So that'd be here. There we are. And that would be B. Okay, so it's asking us to find the equation of C. So AB is the diameter. Okay, so we need it in the form Z minus little a is equal to little b. So A again is the center, so you should know this. A is the center and B is the radius. And I guess that's a little reason why for for anything at all, this modulus, so if you have x minus a, that gives you the distance between point x and point A, okay? So that's the length of the line, the straight line connecting x to A. So the straight line distance between x and A, okay? That's what it means. Now, if it has to be equal to a number, b, wow, what are all the possibilities? So say if A is fixed, so A is here, and X has to be within a distance of B to A. Okay, so this is A, X could be here, X could be here, so this could be B as well. And very quickly, it realised from G to C actually, all these points, all the possible points away from A with length B is a circle of points, right? With radius b away from x. So that represents distance, and if the distance is a number, it will be a circle of points, okay? Because all a radius of b away from a. So hopefully that's kind of clear where that all comes from. But yeah, you should hopefully realise by now that this form here is a circle with centre A and radius B. Notice the minus here becomes a positive. Okay, it's like with circles in normal maths, right? X minus A squared is y minus B squared is R squared. It's kind of similar, and we will be using that actually in the question. Anyway, waffle side, we are given AB as a diameter. Well, if we know the length of A and the length, oh, hang on. Actually, this makes it a bit more clearer. So we need to find the length of AB. Okay. Right. We also know, by the way, if we want to find the center, well, the center is going to be halfway through because half the diameter is the center, and actually the center is going to be the midpoint. So midpoint of AB. Well, you sum the x coordinates. So in here, the x coordinate is the real axis and the y coordinate is imaginary. A is, let's reiterate again, -3 and 2i, and B is going to be 5 and -4i. Okay. So the midpoint, you add the x1s together, so you're going to have 5 -3 over 2, and you're going to have minus 4 add 2 over 2i, right? So you find the midpoint of each x and y coordinate, so the real and the imaginary coordinate, exactly like GCSE. So that would be 1. 5 is 2 over 2, 1. 2 minus 2 over 2, that'd be minus 1i. So minus I. That will be your centre here. So therefore z would be mod z minus 1 plus I would be equal to B. Now we just need to find the B, and B would be the radius, right? So it's going to be the length of the line AB, well, half the length of line AB, or the length between the midpoint and A. Well, that's just Pythagoras, isn't it? So the B, well, I guess the diameter or the length of AB. Let's just say the length AB. That's again from G3 maths, right? The length between 2 points is the Pythagoras distance between them. So difference of the x coordinates are 3 minus 5. That would be plus 3 squared. Uh, plus the y distance, that would be minus 4. Plus minus 2 squared. And that would be the length. Okay, let's put that in the calculator. And that would be 10. Okay. But the length of AB is the diameter. So therefore the radius will be half of that, which would be 5. And that means B is 5. And therefore that completes our equation. So Z minus 1, was it? Plus I is equal to 5. Was that what we got? Yes. Let's check the question. Okay, it doesn't give us that, but I think that's how you do it, right? And yeah, I think just a tip in general as well. I've noticed a few of these geometry questions with complex numbers. They often will consider you to determine diameters and midpoints. So be careful where you might need to work out the midpoint or something. I've seen one question as well, just to say it was to do with roots of unity, and it was like a hexagon, and it gave you the outermost point here and this point here, and it told you to work out the center. Well, the center will just be the midpoint between the two vertices, right? Like exactly like this. And therefore the diameter would be the radius would be half the distance of the line. They do like to really knowing the midpoint of something really just come in handy with geometry questions like this. So just be aware you might need to know that. Okay, that shouldn't be too bad, right? Okay, so we got that. Then it says a circle D with this equation here intersects C at 2 points, 2 complex numbers, and then it says to find them. Well, if we're going to find them exactly, we're going to need to do it algebraically, right? Well, the best way. So we've got this is circle C, and circle D is given to be Z minus 2 minus 3i equals 2. And that's D. And this will be part B as well. Okay. Is that right? Okay, minus 2 minus 3i. Okay, so if they intersect, we're going to need to equate them together, but it's not particularly clear how. But the methodology is, well, say a point is x plus iy, right? Any point z. That means that x plus iy minus 1 plus I equals 5 for c. And that means that if you group them together, x minus 1 plus I of y plus 1 is equal to 5. Okay. And then for the second one, that's c again. And then for the second one, x plus iy minus 2 minus 3i is equal to 2. And that means then, if we group them together, x minus 2 plus I of y minus 3, and that would be equal to 2. That's D. And actually, this is extremely similar now to a circle equation, isn't it? Um, well, what can we do? Well, it turns out we can square both sides of the equations here to get the following. X minus 1 squared plus y plus 1 squared gets us 25. And x minus 2 squared, square this one, plus y minus 3 squared gets us 4. Okay, I'm not going to go too much into that, but that's sort of the methodology, right? And obviously squaring will get rid of the brackets because then it'd be positive by default. It's kind of like a modulus, right? But yeah, that's sort of the methodology behind that. Um, but yeah, I'm not going to go too much into that. I'll explain it at a different time. But that's the method you need to know, right? That you can convert into this form, into Cartesian form like this, into circle form by squaring like this. Okay, and you get rid of the I as well. Well, actually, this is like great news because now we can just work with this and substitute stuff in. No modulus, no i's to worry about. Okay, so I think the best thing is to expand because we're going to need to expand anyway to find x and y. So first equation then that's going to be x squared minus 2x minus plus 1 plus y squared plus 2y plus 1 is 25. Don't think we can really do that. Well, we can simplify the constants, I guess. So x squared plus y, x squared plus y squared minus 2x plus 2y plus 1 plus 1, 2, 25 minus 2 is 23. And then that's equation 1. And then x squared. And then we expand the second one. X squared minus 4x plus 4 plus y squared minus 6y plus 9 equals 4, which then simplifies to x squared plus y squared minus 4x minus 6y. Then 9 add 4 is 13. Take away 4, take away 13 is minus 7. Oh, hang on. No. 4 take away 13 is 9, not 7. I don't know why I thought that. Okay. And that's equation 2. And actually, it's very tricky if you just uh, brainlessly, I guess, for lack of better words, just try to substitute one into the other. You're gonna have a rough time. But the best way to do this is to actually use elimination, right? So we're going to do 1 minus 2. And actually, this gets rid of x squared and y squared. And this will always work for this particular example, right, of complex numbers. Because when z is x plus iy, that means the x and y will always have a coefficient of 1. So that means when we square it at the end, when we do all of this, you'll always have just x minus a number, not 2x or 3x minus a number. It would just be x. And it'd be the exact same for y, for all equations. So this means that at the very end here, when we have x squared and y squared, it will just be x squared and y squared on both of them. So when we subtract the two equations, you will always just have linear stuff at the end. There'll be no squares. Because of this fact here, uh, how we choose the x and y, it will always have a coefficient of 1. Okay, so hopefully that's clear. So don't be afraid. Oh, what about if it doesn't work like this in my exam? It'd be fine. It will always work out this way. So you can always subtract one from the other. So then you're left with minus 2x minus 4. X is just 2x, right? 4x minus 2x would be 2x, and then 2y minus of minus 6y, that'd be plus 8y. And then 23 minus 9 would be 32. 23 add 9. And actually, this gives us a substitution now, a nice one. So you can say x then is 4y. No, hang on, 16 minus 4y to make it nice. So 2x is 32 minus 8y, then divide by 4. Okay, so then sub x into any of them. So let's say sub x into 1. I guess that seems the nicest. Well, then that means 16 minus 4y squared. 4y all squared, sorry. That's x squared. Plus y squared minus 2 lots of x, which is 16 minus 4y. Plus 2y equals 23. And at this point, again, we just expand and simplify. And now, because there's only y here, we can solve for y. So if we expand this out, 16 squared would be 256. That'd be minus 28. 128y plus 16y squared plus y squared minus 32 plus 8y plus 2y is 23. Here, squeeze it in. Therefore, we simplify it. So that's 200. Let's group the y squares together. So 16y squared and y, that'd be 17y squared. Then the y's together, minus 128. Plus 8 plus y, 8 plus 8y plus 2y. We'll be left with minus 118y. And then we group the constants together. So 256 minus 32 minus 23 will get you 201 equals 0. And this is a quadratic for y. So therefore y, you can just plug that into your calculator, I guess. Or if you do want to really cover your back, just write the quadratic formula and then use the calculator. So that's 17 minus 108, 201. And surprisingly, you get quite nice values. So y is 67 over 17, or 3. So again, if you've got quite nice values, you've probably done it right. Okay. Cool, so there are two y values. So therefore, x then, well, we know x is this, right? 16 minus 4y. So x is 16 minus 4 of 67 over 7. 67 over 17 and that'll be 16 minus 4 of 60. Oh, 67 over 17. That'd be 4 over 17. Or x is 16 minus 4 lots of 3, which should be 4. And those are our solutions. So z1 then. So obviously z, remember, is x plus iy. Therefore, z1, what the first solution? Let's take x is 4, so that's going to be 4, and then that'll be when y is 3. And then z2 would be x is 4 over 17. And then add 67 over 17i. And those should be your two solutions there. I want to check this actually. But that's the process, right? You essentially want to expand it into, so you got the circle equations, and then subtract the two equations to solve them simultaneously. And you will be able to solve them simultaneously because of how circles are defined in complex numbers. You don't have to worry about things not cancelling. They should cancel. Okay. Do, 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 do. Yeah, okay, those are the answers. Lovely. 3 plus 4 plus 3i, and 4 over 17 plus 67 over 17. Great, so that's right. Okay, cool. On question 6 now. Okay, we've done most of it now. Now we've got this one. It's actually not okay. It's a nice little breather, actually, this one is. So it's roots of polynomials, clearly. So we've got a cubic equation with roots alpha, beta, gamma. And we've got the shifted equation when the roots are 4a minus 1. And then we need to find a, b, and c, the coefficients on the polynomials. Well, I think probably the way what's screaming us to do is actually to substitute this in. So we know the roots are in the form x is going to be 4w minus 1. Okay. Because if alpha, beta, gamma is a root, so then alpha cubed, and then subbing alpha for x here, and then uh, and then you want to shift the roots to 4 alpha minus 1, where you need to just say x is 4 alpha minus 1 to then substitute that in, and then it will still be a root at the end, so equals 0, and that's where w comes in. Okay, so x is 4, w is 4x minus 1. And actually that's the wrong way around. W is 4x minus 1. And it's actually quite easy to remember the order in it. Where do you put your x and your w? Because, well, x is here, so the root here is x. So really, alpha would be x here. So that means w would be each of these. So w is 4 alpha minus 1. So w has to be 4 x minus 1. Okay. And that's what we're going to do. You can do this two ways, actually. You can, actually, because they're giving you W here, you could substitute W into here. And I think that's the best way to do it, actually. Substitute W is X plus something into there. And then you get back the X quadratic. Uh, uh, okay, what am I saying? Well, we know W is for And that's wrong, by the way. W is 4x minus 1. Well, I think if you substitute this in for x, I think this should boil down uh, to a cubic in x, which is this same one here. And that's what we're going to do. Alternatively, and what the usual method is it asks you to find a new cubic root, and for that you'd need to say that x would be a quarter of w plus 1, right? You rearrange for x in terms of w, then you substitute that in place for x here, and then you get the new cubic for w. But they've actually given us the cubic already, so we actually can work backwards and substitute w to get back in terms of x, and then we can compare the numbers to get the missing values. And that's what we're going to do here. So the cubic is w cubed, was it? W cubed minus 9w squared minus 97w plus c equals 0. And actually, I've chosen this kind of deliberately as well, because if I substitute x into here, it would have a nasty fraction. I mean, that's still quite, you can deal with it still, don't get me wrong, but with this it's linear, right? It's far nicer to write down and expand this in cubic powers than this, okay, than x. So I think it's nicer if you substitute w in instead of x, and then dealing with nasty fractions. But that's what we're going to do here. So we wrote down our cubic for w, so that now we just substitute it for this. Sub w is 4x minus 1, which is the usual approach. And therefore that would be 4x minus 1 cubed minus 9 of 4x minus 1 squared minus 97 4x minus 1 plus c equals 0. And it's just an expand exercise. What I like to do is actually write the expansion here on its own, aside. So I'm going to say, note that 4x minus 1, 4x minus 1, 4x minus 1 is equal to, and then expand the first set of brackets, so that's going to be 16x squared, minus 4x minus 4, that would be minus 8x plus 1, of 4x minus 1. And then that will go to 64x cubed, minus 16x squared, minus 32 x squared plus 8x plus 4x minus 1. And that simplifies to 64x cubed minus 48x squared plus 12x minus 1. So now we can just say, therefore, cubic is this, and then we substitute our result in. So that's 4x minus 1 cubed. So that's going to be 64x cubed minus 48x squared plus 12x minus 1 minus 9, lots of the squared, which is just this bracket here. So minus 9 times 16, that's minus 144 x squared. Minus 9 times minus, that'd be plus 72x. Minus 9. Minus 9 times 1, that would be minus 9. Minus 97 times 4x, that would be minus 388. And then times, add 97 plus c equals 0. Now we can simplify this. So let's bring all the terms together. So 64x cubed. And then minus 48x squared minus another 144 is minus 192. Then plus 12x adds 72x. And then minus 388x gets you minus 304x. And then add the constants. So that'll be minus 1, minus 9, plus 97 plus c. So that'll be 87 plus c. Okay. Now we can compare to the cubic, the x cubic, right? That we were given as well. So that was ax cubed plus bx squared. And actually, it's very easy. We can spot the solution, can't we? Minus 19x minus b. And that would be equal to 0. Cool. So then compare coefficients. It's very easy to spot this, right? A would have to be 64, right? 64x cubed, ax cubed. Then b would have to be minus 192, as you can see there. And what's going on here? Oh, we messed up big time here. That's not right. Minus 304 minus 19. They're not the same in any realm. Where have we gone wrong? That is interesting. I think it's. I don't think we actually can do this actually. Because this is already in W. And this is the root. We're not shifting this by any way, are we? No, we're not. Because this is the same root as this. It's the exact same way. So the quadratics won't, no, they won't match. Whereas here, this is obviously, we're shifting it, right? This is obviously a different way of doing it. But W is 4x minus 1. The root is 4x minus 1. But the roots here are alpha, beta, gamma. But this is not just x, is alpha, beta, gamma. So, yeah, I think that's all wrong, actually. That's a good learning curve, actually. Okay. Tell you what, I'm not going to spend ages rubbing that out. I'm going to redo this again very quickly. So what I'm going to do instead, and what I should have done actually, substitute x in, because what we're doing here is actually shifting the roots to get a shifted cubic. When I'm substituting w's for x minus 1, that's the exact same version, right, of the roots. We are not shifting anything by doing that because it's in the same form as the roots. So this quadratic won't really change. Therefore, if we get it in x, this will not be the same cubic here because we're not shifting it. Whereas here, because the roots are different, we are actively shifting, if we substitute x for w, shifting it into the new quadratic, okay? So we can compare it if we substitute x, but not the other way around. Okay, hopefully I've explained that sort of well. I don't know. But yeah, I should have realised that. But oh well, it's a learning curve, right? Good job we make the mistakes now. So yeah, I guess like the safe way, if you ever get a question like this, always substitute the original quadratic, never the other way around. I guess if that's how you want to learn it. But yeah, that's what we're going to do instead. So we're going to substitute x is a quarter of w, was it? Minus 1. Was that it? W plus 1 into the cubic, right? Into ax cubed, was it, plus bx squared plus 13x, was it? Minus 19x, there we go. Minus b equals 0. Let's get cracking then. So again, like we did before, let's note that the cube of this, so a quarter of w plus 1 times by a quarter of w plus 1 times by a quarter of w plus 1. That's going to be, well, a 16th of, then times the inner bracket, so that's w squared plus 2w plus 1 times by a quarter of w plus 1. It could just factor the quarter out, I guess. So that'd be 1 over 64 of, and then w cubed times in the inner bracket, w cubed plus w squared plus 2w squared plus 2w plus w plus 1. And then let's bring that together, simplify this, w cubed plus 3w squared plus 3w plus 1. And then we're going to use that to rearrange this, okay? Therefore, cubic becomes a lots of this, so it's going to be a over 64 of w cubed plus a over, oh, what's 3 over 64 won't simplify, will it? Nah. Plus 3a over 64 w squared plus 3a. I need to make sure it's clearly an a and not a 9. I know I'm going to misread that as a 9. I know I am. 3a over 64 x squared plus 3a over 64 w. No, w, not x squared. W. W plus a over 64 plus b over x squared, which would be the second bracket, this bracket here, 16th of w squared, so that'd be b over 16 of w squared plus an 8th w b over 8w plus b over 16. So all I've done there is times the squared, this whole quarter w plus 1 squared times by b. So that's all I've done there. And then I'm minus 19x. That's minus 19 of over 4 w minus 19 over 4 minus b equals 0. Then, well, I think the best thing we can do, actually, before we simplify, let's times by 64 to get rid of all these nasty fractions. So then you're going to be left with aw cubed plus 3aw squared plus 3aw plus a plus 4b w squared plus 8bw plus 4b minus 19 over 4 times by 16 minus 76 w minus 76 minus 64b equals 0. Okay, then let's simplify this again. So you're going to have AW cubed. I feel like I made a mistake here somewhere, an arithmetic one. Uh, so to clarify, all I've done here from this bit here to here was times by 64 to get rid of all the fractions. 19 over 4 times 64. Oh, yeah, it's 304, not 76. Yeah, I knew I went somewhere wrong. 304W minus 304 uh, minus 64B. Okay, there we are. So that means AW cubed plus, well, 3AW squared plus 4BW squared. That's going to be plus 3A plus 4B W squared plus 3AW plus, okay, so 3A plus 8B minus 304W. And then let's add the constants together. So that's going to be plus A plus 4B minus 64B equals 0. Right? And then we're going to do the same sort of process again. So we're going to compare to the other cubic, which was W cubed minus 9W squared minus 97W plus C equals 0. And hopefully this time it's consistent. Okay, so therefore, well, obviously AW cubed is W, so A has to be 1. Okay, and therefore minus 9, if you write it down here, minus 9 has to be matching to the W squared coefficient, so 3A plus 4B, or 4B, which therefore means that B is minus a quarter of minus 9 minus 3 lots of 1, and that will be minus 9 minus 3. That'd be minus 3. Then to C, and therefore C then has to be the constant bit, so it's going to be A plus 4B minus 64B. That's going to be 3 minus 60B. That's going to be minus 3, and that's going to be 183. So those should be your values A, B, C. I do want to check that actually. Is that right? Please say it is. For fuck's sake, no, it's not. What have I done wrong? Okay. So A's 4, apparently. It's probably something to do with my expanding or something. I don't know. Okay, let's see what the mark scheme's doing now. So X is a quarter, W plus 1. That's what we did. Yep. What should be a problem by expanding? Watch. So then an A, lots of, yep, minus 19, minus B. So you're left with AW cubed plus 3A plus 4BW squared plus 3A plus 8b minus 304. Yep. A, oh, plus A minus 60b. Oh, minus 304. Yes, because there's a constant here. A plus 4b minus 64 minus 304. But that still won't change my. That still won't be right. That won't magically solve it. Okay. Okay, what does it do after this? Divides by A and equates to coefficients of. What do you mean divides by A? That's why. Ah. God, that's nasty. That is nasty from them. Okay. So, what's happened here is, let's see, even I'm learning here. So I haven't seen this question before, so I'm doing it first time as well. Obviously somebody might have clocked. That's good. But this is so we need to essentially compare to the cubic, which we've done. But it's pretty nasty for them to make you have to realise this. But essentially these cubics are still differing by a multiple of A. Because obviously it's an equation equal to 0. What they've probably done here is this was a multiple of A, but then they divided it F it by A, which you can do, and then they simplified the cubic to just W cubed. What they and this is where this is iffy for me. I'm not gonna lie, it's a bit naughty about Excel to not hint at this, but essentially you need to divide this cubic to match this one. So they're not exactly the same. They're still different by a scale factor, by a multiple. So you need to make sure that to compare them, they have the same first term, W cubed. To do that, you either need to times this by A, or you need to divide this by A. So divide top cubic. So I'm going to say divide cubic by A. And then we get W cubed plus 3A plus 4B over A, W squared, plus 3A plus 8B minus 304 over A, W, and then plus A minus 60B minus 304 over A equals 0. And then it matches this, okay? But there's no in the question that hits for you to normally I think a lot of people do what I did and just take A to be 1 and then compare it that way. But I think the idea is because there's 4 equations with 3 unknowns. Obviously, like we said, that like we just did. This is just me spitballing now. What's it called? Um, you won't get there'll be no solutions, like we just said. So, hmm. Okay, so that's what you need to factor in when you do these questions. That there will be they can. Let me read the question. Why is there a scale factor there? There's no hint towards that. The cubic equation has roots of this. Okay. So yeah, I guess. Okay. So okay. So normally, when you do cubic these roots of polynomial questions, they normally ask you to find a cubic equation or polynomial with roots, say for example, 4 alpha minus 1, 4 beta minus 1, 4 gamma by the minus 1. That's my horrible gamma. But it says A. So you know when you substitute x into here to get in terms of w, that that doesn't have to be the same equation here. What you found here, when you substitute x into there, into the equation, and you get w a cubic, that's a cubic. But but you can find infinitely many by scaling it, because obviously you can divide both sides by the same number, and you can scale it. So what you need to do is, because it says it's giving you a cubic equation. So if you're going to compare them, then they need to be the same, and you need to rather than, but uh, but as I said, because there's 4 terms, that will give you if you compare each coefficient, you'll get 4 equations. But we only have 3 unknowns here. So to make this solvable, we need to make sure that we have two 1 term matching. So if we divide the a, so what I'm saying here is if we account for the scale factor by dividing by a, and then it's w cubed on both of them here, we now only have 3 equations and 3 unknowns. So this can be solved. And now this has to. I guess it's kind of like ratios in a way. So it's like 2 to 4 is 1 to 2. But say if I had 4 slices of the pizza and I had 2 of them. In actuality, there are 4 slices, not two. But actually, this is equivalent, but that's not identical. Okay, so these are equivalent cubics, but they're not identical, which means again we need to scale up by a scale factor, divide or multiply by a scale factor to make them identical, and that's what we're doing here. So that's the thing you need to pay attention to when you are when you're doing roots. When you're substituting a different a shift. So x is a quarter of w plus 1. When you are substituting that into your x polynomial, your original polynomial, when you get that when you then get a cubic for w, you're just getting one particular cubic. Um, but they can give you a different cubic, and you do need to scale it. So that's something roots polynomials. Okay. Yeah, I wasn't aware of that until just now, actually. Just popped into my mind after looking at the mark scheme. But yeah, that's a very nasty question. I don't think a lot of people would pay attention to that. I don't know. I would, but then I got obviously then I got wrong answer, so I thought, oh, something's not right here. But what you need to pay attention to this topic. It's a good learning. This is really it teaches you a lot actually. Um, be aware that there's actually multiple cubics, or infinitely many cubics that will have the shifted roots. To make sure you get the identical one, kind of like ratios, you will need to divide through to make the terms equal. Okay, so you can't equate them just yet. So we need to divide through to at least make the w cubes match. Anyway, we've done all that, so now we can equate because they're identical polynomials. Therefore, equating coefficients now. I'd love to see examiner's report on that question. I'd love to see how many people actually got that question. Anyway, so equating coefficients. Well, the xw cube is going to be the same. So 3a plus 4b over a, and that's going to be equal to -9. Therefore, we can say that 3a plus 4b is minus 9a. So a in terms of b would be, well, 12a is 4b, which means a is, well, b, I guess, in nice terms, is 3a. Okay, that's one equation. Now let's look at the other one. So then we have, and 3a plus 8b minus 304 over a. That has to be equal to minus 97. And then we can substitute our place for b. So therefore 3a plus 24 lots of a for 8b minus 304 is minus 97a. And now we have an equation for a, which we can solve. And hopefully this time we get the right answer. So 124a is 304. Therefore, a is 304 divided by 124. Hang on. What's happening here? Uh, 3a plus 8, 16, 24. Okay, I'm getting a different answer to the mark scheme again. Why? Uh, 304 divided by 124. They've got a's 4 here. Okay, they've got the equal 3a plus 8b minus 304 over a is minus 97. And 3a plus 4b over a is minus 9. So they've got the two equations here. So how on earth did I get the wrong value here for a? Oh, hang on. Oh, hang on. Oh, that's bloody what? Negatives. Oh my god. 12a minus 4b. Yes. Oh my lord. So b's minus 3a. Oh man. Oh, okay. So then that'd be minus 24a. So then that leaves us with 76a, is it? 100 minus 24 is 76. And hopefully, okay, now we can solve it, right? We get 4. Okay, that's the answer they were looking for. There we go, 4. Then therefore that means B is minus 3 of 4, which should be minus 12. Okay, and now we can find C. So C then, and it's going to be this constant here. So it's going to be A, A is 4, minus 60 of minus 12 would be, minus 304 over 4, and that will give us 105. And that's what they got. That is probably one of the worst roots of polynomial questions I've ever seen, ever. That is disgusting. That question is. Oh my lord. But we finally got there in the end. I'm tempted now that I've done it for the first time and I've worked through it. I'm tempted maybe to explain it again, go over it tomorrow again, in a bit, because I know what the question's about now. But I don't know if that's someone's interested in. I can go over that tomorrow because there will be a roots of polynomials question, and I think this is a really good way to really test your understanding of roots of polynomials. But that is an absolutely vile question. Okay, we're on the next part now. In this question, you may assume results for the sum of our cube, okay, as usual. So show that the sum of the cubes of the first n positive numbers is that. Okay, so how do we phrase this? So, well, sum of the first cube, oh, hang on, let's get it again. Sum of the cubes of the first n odd numbers, right? Of the first odd number. Well, the cube of an odd number is of the form 2r minus 1. The cube of that is cubed. And we want the sum. So that's going to be between r is 1 and n, because it's first n. So that's so once you express that in terms of series notation, oh, hang on, 2r minus 1 all cubed. Okay, once you've hopefully you realise that's an odd number cubed, and you're summing the first n of them. Okay, so that's that in series notation. So again, we're going to need to expand 2r minus 1 cubed, and then we can use our standard results and substitute it in. So again, note that 2r minus 1, 2r minus 1, 2r minus 1 is going to be equal to 4r squared minus 4r plus 1, 2r minus 1, which is 8r cubed minus 4r squared minus 8r plus 4r plus 2r minus 1, which simplifies to 8r cubed if it deletes. There we are. 8r cubed minus 4r squared. Hang on, am I missing another squared? Let me check. 8r cubed minus 4r squared minus 8r squared. There we are. Plus 4r plus 2r minus, okay. So that'd be minus 12r squared plus 6r minus 1. So therefore the sum, we substitute this result in, is going to be between n and r is 1 of 8r cubed minus 12r squared plus 6r minus 1. And then we can split this up, so we can say that's 8 lots of r cubed minus 12 lots of r squared plus 6 lots of r minus 1 lots of that, okay. And so we can substitute our results in. So we can substitute n r is 1 of r, which is a half r plus 1. That I think you do need to know, but yeah. And then the sum of r equals 1 to n of r squared is a 6th n of n plus 1, 2n plus 1. It's in the formula book, that one is. And yeah, cool. By the way, if you do struggle to work this out, well, observe that for r, by the way, because you don't give you the sum for r. This is the arithmetic sequence 1 plus 2 plus 3 plus 4. So the common difference is what the first term is 1, r is 1. Then you can use Sn to work out an expression for in terms of n. So that would be n plus n over 2 n minus 1. Well, you can actually keep the half out actually, because it's keep the half out. That'd be a half of 2n No, sorry, 2n plus n squared minus n. That'll go to a half of n squared plus n, which should be a half n of n plus 1. So there is a way to derive r, by the way, if you do somehow forget it, just a rough little sketch there, using the A-level method, or otherwise. But hopefully you should really remember that though. I'm surprised I don't give you that, but yeah, that's the way to if quickly, roughly derive it if you ever stuck. Anyway, but I'm gonna stop waffling now. So let's just recall the standard results, which should then be a fourth n squared n plus 1 squared. This should be n, by the way, not r. Okay, so now we literally substitute this in. So the sum is going to be 8 lots of r cubed. So it's going to be 8. Well, 8 over 4. That's going to be 2. And then minus 12 over 6, that's minus 2, n, 2n plus 1, plus 6 lots of r, that would be plus 3n, n plus 1, and minus 1, so that's going to be just minus n, because you're adding 1 n times, so that'd be n in here, and then that'd be minus n. Then we just need to expand some stuff, so that'll be 2n squared of Uh, well, actually, immediately I notice n is a factor of everything, actually. So n, and bring that out, so that's going to be 2n, n plus 1 squared, minus 2n plus 1, 2n plus 1, plus 3n plus 1, minus n. And then I notice, again, there's n plus 1 is common to everything, because watch this. Cool. And then if you expand this, that'd be 3n plus 3 minus n. Oh, hang on. Oh, actually, no, that'd be 2n minus 3. Okay, never mind. What form does it want us in it to write it in? Let's have a look. N squared. Okay, so we're going to need to factor an n squared out. Okay, so we need another n here. I do think the only way we're going to be able to do that is to expand this out. I think. So n of 2n of n squared plus 2n plus 1 minus 2 lots of 2n squared plus n plus 2, that'd be plus 3n plus 1 plus 2n minus 3. It's not too bad, I guess. So n of 2n cubed plus 4n squared plus 2n minus 4n squared minus 6n minus 2 plus 2n minus 3. And that's going to be n of 2n cubed, and then the n squares cancel. 4n minus, that'd be minus 2n minus 5. Okay, well, we've gone wrong here because we need to factor another n out. So what has happened here? Probably a negative somewhere. Let's have a look. Is this expansion right, first of all? Minus 4r squared minus 8r squared plus 4r plus 2r minus. Okay, that should be fine. So is this right then? 8 cubed minus 12. Okay. Okay, so the sum then would be 8 lots of r cubed, so it'd be 8 over 4, which would be 2, n squared of n plus 1 squared, minus 12 over 6, should be 2n of n plus 1, 2n plus 1, plus 6 lots of r, so that'd be 6 of a half, so that'd be 6, that'd be 3n of n plus 1, minus n. So you can factor an n out, and then that'd be 2n, n plus 1 squared, minus 2n plus 1, 2n plus 1, plus 3n plus 1, minus... Ah! That's why. It's meant to be minus 1. Because we already factored the n out, so that would be minus 1. Okay. Plus 3n, plus 3, plus 2. Okay. So it's the other way around. Does that help us by any way though? Anyway, that'll go to plus 3n plus 2. So then that'd be 2n cubed plus 4n squared plus 2n minus 4n squared minus 6n minus 2 plus 3n minus 2. 3n plus 2, sorry. Oh, the 2's cancel. Lovely. Okay, so we have no constant. So it'd be 2n cubed plus 2n plus 5n minus 6. So I'd be left with just minus n. There we go. Okay. Yeah, bloody hell. There we are. And then we can factor another n out. So n squared of 2n minus 1. 2n squared. And that, I believe, is part A, right? There we go. Then it says the sum of the cubes of 10 consecutive prime odd numbers is 99800. Find the smallest of these numbers. So we basically now need to substitute a value of n. So the sum has to be now between r is a number n of obviously 2r minus 1 cubed. But it needs to be the first 10 numbers. So n is so when n, that's the first number. So then n plus 9 actually would be the 10th number. I guess the way to think of it is, say if n is 1, so that's like the first odd number. Well, 1 plus 9 would be 10, and that would be the 10th number, right? I guess some people would think n plus 10, but then that would go over by 1, because then that'd be the 11th odd number, not the 10th. So just be careful of that. So yeah, so now we just need to evaluate this. Well, actually, like we know how to we can only use our results when r is 1 to n. So we need to shift this from starting to 1 to n plus 9 of 2r minus 1 cubed minus, and then r is 1 to n minus 1. Okay. Uh, and that's what we're going to do. And so then we're going to substitute these results in. So we found in part A, that this sum is equivalent to this. So we substitute n plus 9 for n. So that's going to be n plus 9 squared of 2 of n plus 9 squared minus 1 minus n minus 1 squared of 2 of n minus 1 squared minus 1. And we can simplify this before we equate anything. We're going to have to expand it out, aren't we? We can't really factor anything out, not nicely. So that's going to be n squared plus 18n plus 81 of 2 lots of this. So it's going to be 2n squared plus 36n plus 162 minus 1, so that'd be 161 minus n squared minus 2n plus 1 of 2 lots of that, 2n squared minus 4n plus 2 minus 1, that'd be plus 1. I don't want to expand that out. How many marks is it? Is that maybe there might be a way? 4. Okay. Because really, all we got to do then is equate this to a number 99800 and then solve it. Obviously, I think they expect you can use your calculator to solve it, but uh, we're gonna have to expand it out. Come on, this is the systematic way. Okay, so okay, let me check. Do these have any common factors? Let me check actually. Let's because these obviously factorize to n minus 1 and n plus 9. What about these? Let me check. Uh, 'Cause we might like this is the only way to simplify it if we can. Yeah, this first bracket here, nah, nasty roots. Doesn't factorize. Then we have 2 minus 4 and 1. Yep, both of them. Yeah, not the other two brackets don't factor. We have to expand it out. There's no way we can simplify it. Okay, here we go. So 2n to the 4 plus 36n cubed plus 161n squared plus 36 n cubed plus 18 times 36, which is 648 n squared plus 18 times 161 2898 n plus 81 162 n squared plus 81 times 36 2916 n plus 161 times 81, which is this number here, 13041. And then we're going to be minusing with the expansion of this, so it's going to be 2n to the 4. Well, at least the 4's cancel. We can deal with cubics, I think. 2n to the 4 minus 4n cubed plus n squared minus 4n cubed plus 8n squared minus 2n plus 2n squared minus 4n plus 1. Okay, that wasn't too bad. So now we could just take them away. But actually, let's simplify both parts. So 2n to the 4 plus, how many n cubes have we got? 36 n cubed, 36 n cubed, that'd be 72 n cubed. Plus n squared, so plus 161 n squared plus 648 plus 162. That'll be 791. 971 x squared. N. God, I'm losing it now. N squared. Oh, what time is it? 120. Okay. That'd be N squared. Then we add the N's. 2898 plus 2916. That'd be plus 5814N plus 13041 minus 2n to the 4 minus 8n cubed plus n squared to 3n squared plus 11n squared minus 2 minus 4, that'd be minus 6n plus 1. Okay, now let's subtract them together. So that's be 2 minus, okay, they go away. So 72 minus plus 8 would be 80n cubed. But 971 n squared minus 11n squared, that would be 960. Then 5814 n plus 6. That'd be 5820. And then minus then 13041 minus 1 is 13040, and that'd be well. It's not. We're going to equate it then to. This is going to be equal to now. Finally, we got through all of that. That's going to be equal to 99800. Okay. And if we've done it right, which I'm a bit skeptical at this point, 99800, we should get a positive integer solution for n. So that means then 80n cubed plus 960n squared plus 5820n plus 13040 minus 99800 is minus 86760 equals 0. Therefore, n, put that into your calculator. You're going to want the cubic solver, so 80, 960, 4820 minus 86760. Okay, you get n is 6, or n is a complex number, or n is complex numbers. So it's like n is minus 9 plus or minus 9 point blah 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 99i. So n is 6. There we go. So okay, that must be right then. Okay, so that's a solution for n. But let's have a look what the question said. Determine the smallest of these 10 consecutive prime numbers. So remember the smallest one, so the first value was summing, was actually r to equals n. So actually r is the what's it, the smallest odd number. Well, yeah, the odd number, remember, we're substituting r is n, so the smallest odd number. That's going to be 2r minus 1 for n, so it's going to be 2 of 6 minus 1. That's going to be 11. Okay. Let me double check that. Oh man. What a bloody question. Uh, where's that question from? Okay. Okay, I've got two more questions left. However, I'm going to do this vector one, but then there's a massive differential equation question. I'll be doing that tomorrow. But I'll leave it the vector one. But yeah. Yeah. So it's 20, 20, 21, paper two. Yeah. The smallest number is 11. Yeah, so I got that right. 4 marks. I swear to God. I think further maths sometimes it's just a test of like your algebra skills and not how quick you can do it in, rather than actual math knowledge. I don't know. Is that just me? I don't know. Uh, okay. Uh, okay. Question 8, the final question we're doing today, and then we'll move the other question on. By the way, this is about like 85 marks worth of questions. By the way. So it's a bit over a paper. So if we do these 8 questions, this is more or less a whole paper. So this is good. This is basically a practice paper with obviously walkthroughs and stuff like that. So it's going to be longer, but that's because I'm explaining it and going in depth. Okay, now actually this one I did on my stream yesterday, 2023 paper one. Now there wasn't a vectors question, so there will be a vectors question in your paper. But I think this is a good one to test your knowledge on vectors. Okay, so we have a line L1 and we have a plane. So it's asking us to find the intersection of L1 and plane pi 1. Now, actually, you should recognize all of these in Cartesian form of a line equals the direction parameter lambda. And you can notice this in your formula book. Uh, which is here. I've already done it because I did it earlier. Yesterday even. Yeah, so this is lambda. This is the Cartesian form. So really, if we find the intersection of the point and the plane, I think we can substitute. We can find lambda in terms of x, y, and z, and then substitute it in to find lambda, and then resubstitute it for x, y, and z. I think that's the good strategy here. So let's do that then. So part A, x plus 5 equals lambda. No, oh God, even my laptop's giving up now. X plus 5 is lambda, and then y, y plus 4 over minus 3. So y plus 4 is minus 3 lambda, and then z minus 3 equals 5 lambda. Okay, so that's just equating every fraction to lambda. Therefore, we need to substitute x, y, and z. So x is lambda minus 5, y would be minus 4 minus 3 lambda, and then z would be 3 plus 5 lambda. So therefore, the plane equation, which is 2x plus 3y minus 2z is 6. Becomes 2 of lambda minus 5 plus 3 of minus 4 minus 3 lambda minus 2 of 3 plus 5 lambda equals 6. And that's going to be, well, if we expand it to lambda, minus 10, minus 12, minus 9 lambda, minus 6, minus 10 lambda is equal to 6. And then get the lambdas on this side. So let's put the lambdas on the right hand side actually. So 17 lambda would have to be minus 22, minus 28, minus 34. Therefore, lambda is minus 2. Therefore, then x is lambda minus 5. So that's going to be minus 7. Y is minus 4 minus 3 lambda. So minus 4 plus 6. That's going to be 2. Then z is going to be 3 minus 10. That's going to be minus 7. So therefore, the point is simply minus 7 to minus 7. That's the point of intersection. Cool. Yes, so that's the idea. When you when a plane or a point in not a point, a planar or a line intersect, you just equate the equations together, right? Okay, now it says the line L2 is the reflection of L1 in the plane pi 1. So this is what's happening. And it says to find the line L2. So we have a plane here, and then L1 hits the plane, and then L2 will go away from it. I guess that should make this a bit more clearer. The plane looks like that, I guess. L1, so that's pi 1. That's L1, and obviously that would then continue that way. And then L2 reflects, and then L2 would go that way. So L2 is the reflection of L1 in pi 1, like a mirror line, right? And that's why I equate, and that's our purpose is to find the equation of L2. So L2 will have the form R is a point P plus mu D with a direction vector D. That is just a general form of a line. So what we need to do is to find a point and the direction vector. But we already know a point, don't we? Because the point where L1 intersects pi 1, that is the same point where L2 intersects it as well. So L2 is the same intersection as when L1 and pi 1 cross as well. But did we not already just find the point of intersection between L1 and pi 1 in part A? Yes, we did. So that is the same point that can be on L2. So P here is going to be minus 7 to minus 7. So therefore, R is minus 7 to minus 7 plus mu D. Okay, now actually, if you remember to find a direction vector, if we find another point on L2, if we subtract the 2 points together, we get the direction vector. So all we need to do now to reflect is to find another point on L2. Now, how can we do this? Well, if we pick up any point on Q1, on Q1, L1 to Q, if we reflect the point and then the mirror point Q dash, if we can find this given point on the mirror on the line L2, the reflection of a point on L1, then we can find the direction vector because now we have 2 points. So let's see what's happening here. So remember from G to C or whatever, if we have a point here, if you reflect the point, it's going, and this is Q, and that's Q dash. That's going to be perpendicular to the line, right? The reflection, the line you're reflecting it over, the plane, if you will. So that's perpendicular, and that's what's happening here, right? Here, the Q to Q dash, the line connecting the mirror points is perpendicular to the plane. So I think the strategy here is to find the line Q to Q dash. Okay, so what we need is to, in order to find Q dash, we're going to need Q, aren't we? But Q, it doesn't matter. It's a general strategy. This works for any line, any point on L1. So we need to find any point on L1 to reflect. Okay, so any point at all. Remember L1 is to reiterate, L1 is R is. It gave us the equation, didn't it? In the question, R is. Well, I'm going to write this Cartesian in vector form, so that will be -5 -5 -4 3 plus lambda, lots of what was it? 1 1 minus 3 5. Okay. So you should know how to convert to Cartesian to the vector form, and actually that's also in the formula book if you are stuck to remember. It's here, right? So it tells you the position vector. That means the point on the line, right? Is a point. So a point on the line is A1, A2, A3. The point would be the point corresponds to minus A1, minus A2, minus A3, and the direction vector components are on the denominator, right? So this is direction vector B. So that's how you can deduce the Cartesian form to the vector form, or vice versa. Anyway, we found L1, so we need to find any point on L1. So let's take lambda equals 0, for instance. Okay, you can pick any value of lambda. So let's keep it simple. So therefore, R is going to be -5 -4 3, and that's going to be equal to Q. That's our point. Okay. Now we're going to reflect this. So we're going to use this sort of diagram here to help us show what's going on here. So we have a point on Q, but actually to find the line QQ dash, we already know another point because L1. This is hang on. So the line QQ dash, right? We know a point on the line, right? Which is this. So this is why we found Q, to find a point on QQ dash. So that's going to be R again. A general point of a line, remember, is P plus lambda D. So we need a point vector, position vector, and a direction vector. This is our point Q. So that's going to be -5 -4 3. And then we're going to add by a parameter T, lots of a direction vector. Okay. But we know that by how reflections work. So even think back to GCSE, how you have to reflect a point on the mirror line in like the four quadrant grid. You know those questions where they ask you to reflect a triangle in like the line y is x or something, and then label it t dash. That sort of thing from GCSE, right? Transformations, right? You reflect the points perpendicular to the reflection line. That's how it works, right? But actually, this line then, by how it has to be perpendicular to the plane because this is pi one. Remember the mirror line, what reflecting it over. But we know what the perpendicular vector to pi one is, so therefore that has to be the same direction as the perpendicular to pi one. Isn't the equation of pi one right here 2x plus 3y minus 2z is 6, which was in the question. So therefore, the normal vector of n1, that's going to be 2, 3 minus 2, is it not? So that is going to be the direction vector for QQ dash. So R is going to be minus 5, minus 4, 3, plus T of 2, 3 minus 2. Okay, so now we found the line. So now why is this useful? Well, actually, we can now find, because we know what pi 1 is as well, I think we can substitute this line with the equation of the plane to find the intersection point. Because the idea behind this is this Q occurs when this parameter T is 0, right? If we can find what the parameter is at the intersection point, notice these are equal distances away. If we can find what T is at this point, to get from Q to the intersection is T. So then I get from Q to Q dash would be double the distance. So T would be 2 times the distance, right? So if we can find so the intersection point, remember, was -7 to -7, and we're going to equate that then to the so it's going to be on this. Hang on, no, it won't be on the line. Sorry, hang on. No, we're going to equate this with the equation of the plane, right? So remember x, y, z then. So we equated it with the plane. So that's going to be -5 plus 2t, -4 plus 3t, 3 minus 2t. And now we're going to substitute that into the equation of the plane. So we're going to sub into pi 1. And so that are two lots of x, which are going to be 2 minus 5 plus 2t, plus 3y, which is -4 plus 3t, minus 2z, which is going to be 3 minus 2t, is going to be equal to 6. And then we solve for t, so expand this out, -10 plus 4t, -12 plus 9t, -6 plus 4t equals 6. Okay, so 4t, add 8t, add 9t, it's 17t. That's going to be my 10 add 6, add 6, so 12, 34. So t's 2. Okay, looks very similar to the first question, but I guess t is positive 2, not negative 2. Anyway, so that means t is 2. So that's telling you to get from Q to the intersection, we need to take 2 steps almost, right? It goes from 0 to 2. Therefore, to get from Q to Q dash is double that. So it's going to be T is 4. So we need to substitute T is 4. So that means Q dash then, the point on L2 that we need is going to be -5 plus 2 lots of 4, -4 plus 3 lots of 4, and uh, 3 plus minus, sorry, 3 minus 2 lots of 4, and that's going to be 8 minus 5, that'd be 3, 12 minus 4 would be 8, 3 minus 8, that'd be -5, wouldn't it? Yeah, 3 minus 2, 4. Cool, so that's all right. So now we found the point Q, and now we know 2 points on L2. We know this point P, which was the intersection between L1 and pi 1, and we know a reflected point Q. So that means the direction vector D is going to be, say, Q minus P. And that's going to be 3, 8 minus 5 minus, what was it, minus 7, 2 minus 7? Was that P? The intersection point in part A? Yes, it was. Okay. So therefore that's going to be 3, 10, 6, 2. And so therefore R is going to be minus 7, 2 minus 7. Add mu lots of D. So it's going to be 10, 6, 2. And actually, I believe this is what they wanted us to show. So the reflected L2, which is the reflection of L1 in the plane, is minus 7, 2 minus 7, and mu lots of 10, 6, 2. Lovely, lovely. Okay, so that's how you do reflections, right? If it ever does come up. So you find the intersection point between, let's go back to the diagram. You find the intersection point between L1 and pi 1, the original line and the plane, because that point will also be on L2, okay, the reflected line. Then you need to find any point on L1 and reflect it using this. And then you find the line that joins Q and the reflected point, noting that this will be perpendicular to the plane. Then that has to be the same direction to the normal, so then that allows you to easily find the line of connecting the 2 points. Then you find the point Q dash as a result of that by noting your parameters, right, and doubling it. Then once you've found the point, 2 points, which is the intersection and the reflected point, find the direction, and because you already know a point on the line, then you find your reflection by adding the direction vector to the point. Lovely, lovely. So that's how you approach some type of reflection questions. I might go, if I ever do like a topic videos at some point, obviously it's a bit late now for 2025, sadly, but at any point I'll go in more detail with that perhaps, but that's just the general method, right? The general bit reasoning behind it, okay? So now we're told that plane pi 2 contains line L1 and L2. Determine the vector equation of the line of intersection of pi 1 and pi 2. Okay. So what's happening here is uh, we are told a plane pi 2 contains line 1 and line 2, right? So this is line 2 and line 1, for instance, and this is all in pi 2. This is all, pi 2 kind of engulfs both lines. Because remember, how a plane is formed is essentially composing two lines together. Because these two will be the parallel vectors in pi 2. That's how you form a plane, is by basically composing two different lines together. That's how planes are formed, okay? So so it has these two lines. And what's also happening is the line of intersection of pi 2, uh, this line of intersection then, a different line, L3, is in both L2 and pi 2 and pi 1. So L3 in pi 1 and pi 2. So that means L3 is also contained in like these two different planes, pi 1 and pi 2, right? As so, like they're in like the wedge. Like this line is in like the wedge between pi 1 and pi 2. Okay. So that's L3 there. You see that little line there. So line 3, which is the line of intersection of pi 1 and pi 2, when they both intersect, they intersect at a line, as shown. And yeah, so line 3 will be in pi 1 and pi 2. So how do we determine the equation of L3? Well, again, consider the general form. R is P plus, let's say KD. for the constant k, the scalar. We need a point and a direction vector. Well, because pi2 contains all of L1, and remember L1 and pi1 intersect, that means pi2 will also intersect with pi1 at the point -7 to -7, which remember is when L1 and pi1 intersect, okay? So because pi2 contains all of L1, it will also be there when L1 intersects with anything. So when L1 intersects pi1 at this point here, that means that will also be on pi2. And what that also means as a result is because because this vector equation is contained in pi1 and pi2, then it has to be hang on. Yeah, then this has to be a point on L3 as well. Because remember, pi1 and pi2 will intersect at this point. Well, this is one of the points that intersect. So pi1 and pi2 will have to intersect at this point because of what I said, because L1 is in pi2. So as L1 intersects with pi1 at the point, then so will pi2 with pi1. The plane pi2 with the plane pi1. So that, and we know pi2 and pi1 intersect on this line. So if they intersect at this point, then surely that means this point lies on the line. So this is one of the points that we know actually, which is -7 to -7 plus kd. Okay, hopefully you can kind of wrap your head around that. So that's one of the points on this little line here. Okay, of the line of intersection of the two planes. If we know one point of intersection of the two planes, then that has to also lie on the line of intersection. Okay, now we need to find this direction vector. So this is where now it gets really tricky. And this is where I'm going to go off spec a little bit actually, because I think this is the best way to do it, the most intuitive way to do it. Okay, so we need to find the direction vector. Now, I've already said the vector line L3, which is the line of intersection, that lies on both pi1 and pi2. Now, pi1 and pi2 both have normal vectors, don't they? Right? And because if a line is contained in a plane, it's parallel to the plane, which means it's perpendicular to the normal vector of the plane. Now, because it's because there's it's parallel in both planes, that means we're going to be parallel to both the normal vector of pi2 and the normal vector of pi1. So D is perpendicular to n1 and n2, where n1 and n2 are the perpendicular, the normal vectors of plane 1 and plane 2 respectively. Okay, but we know n1 is, they've given us the equation already of plane 1, the Cartesian form. The normal was here, right? It was 2, 3 minus 2. 2, 3 minus 2. But n2, we don't know n2. We don't have an explicit equation, Cartesian equation for pi2. So how do we find the normal vector of pi2 to then find d? How do we do this? Well, I'm going to explain something called the cross product. So the cross product gives us a vector n. If we have if we know a vector, if we have two vectors, v1 and v2, that are both parallel, that are both perpendicular to a different vector, to a vector n. Then we can find n by doing this 3 by 3 determinant of ijk of V1. How do I want to express this? The obviously the I component of V1, so that's V1x, V1y, V1z, V2x, V2y, V2z. Okay. 3 by 3 determinant. I'll show you what I will show that in practice as we go with this question. But the whole idea of this cross product is if we want to find a vector that's perpendicular to two other vectors, we can use this cross product. It very easily gives us that vector. So what we can say then is why this is useful here, and this is why I really recommend learning it for corporeal vectors even, because it comes so in handy when you have two vectors and you need to find one that's perpendicular to both. So we know we have D, which is perpendicular, as we discussed, to the normal vectors of both planes. If we know both of these vectors, we can substitute n1 and n2 into this cross product to give us D here, right? D would equal the cross product of n1 and n2, and that would give us a vector. But we need to find n2. But let's have a look at pi 2. Well, it said pi 2, if you remember here, it said in the question, pi 2, line L1 and L2 lies in pi 2. Now, L1 has a direction vector and L2 has a direction vector, and these two direction vectors will be perpendicular to the normal vector n2. So we can find n2 by doing the cross product of the direction of L1 and the direction of L2, because it would be perpendicular to both the vectors, okay? And then we could substitute find n2 to then find the direction vector D for the line of intersection. Okay, so n2 ijk, that would be always the same, because that ensures we get a vector. That's why I put ijk there. There we go. And then L1, the direction vector of L1 was -5, -4, 3. That was given in the question. So how you did is you put -5, -4, 3. And then the second one, the direction vector of L2, which we just found, that is 10, 6, 2. And then we just compute the determinant, right? Like using your matrix knowledge. So it's going to be I of -4, 3, 6, 2 plus minus j of, that has to be determinant, doesn't it? There we go. Minus j of -5, 10, 3, 2 plus k of -5, -4, 10, 6. And then compute that. I of, that's going to be -4, that'd be -8, -18. That'd be -26, right? Plus minus j of -10, -30, that'd be -40. Plus k of -30, add 40, that'd be 10. If you just remember how the 2 by 2 determinants work, and therefore the vector n2 is -26, -40, and 10. And actually, we could factor a number out because it's a direction vector. We don't care about the scalar multiple. We just care about the direction itself. So I believe 2 common factor. That's a 5, -20, and -13. And I think we can't simplify that anymore. So keep the number small. So then we have n2. Now, as we just discussed, the direction vector, because L1, L3, sorry, the intersection line lies on both pi1 and pi2, it will have to be perpendicular to the normal vectors, right? Because it's parallel to both planes, so it has to be perpendicular to the normal vectors of both of them. So we can use another cross product to then say D is the ijk of n1, which was 2, 3 minus 2, and then n2, which is minus 13, minus 20, and 5. And that would be I of 3 minus 20 minus 2 of 5 minus j of 2 minus 13 minus 2 of 5 plus k of 2 minus 13, 3 and minus 20. And that will be I of 3 times 15 minus 20 minus 40. 15 minus 40 would be minus 25. And then minus j of 10 minus 26. It should be minus 16. And if I remember doing this question, and I think we messed up somewhere, an arithmetic error. What have we done? Okay. So N2, so that's been normal to L1 and L2. Uh, so I think I've done an arithmetic error here. I think I of minus 4362 minus 8. Did I copy it down right? Have I got the right direction vectors? 1 minus 3, 5. Oh, wow. Wait, what? No, that's not the right direction vector. L1, the direction vector of L1 is 1 minus 3, 5. Where did minus 5, minus 4, and 3 come from? That's not the direction vector of L1. Okay, that's probably why. That's the wrong answer. What? Okay, so let's go back. So that's the method, right? I just copied the wrong numbers for some bloody reason. So 1 minus 3 and 5, okay? Then we're going to compute the determinant there, so it's going to be minus 3, 2, 5 and 6. And then minus j of 110, 5 and 2. And I'll just write the L2 direction vector is 10, 6, 2. Okay, so we're substituting the vectors into there, okay? The right ones anyway. Because one's then plus k, 110, minus 3 and 6. And then hopefully you get the right vector this time. So that'd be I of 6 add 30, that'd be 36. Minus j of 2 minus 50, that'd be minus 48. And then k of 6 minus 30, 6 add 30, that'd be 36. So then the direction vector then is actually 36. 48, because minus j minus 48. And then that's 36. And that simplifies actually nicely to, well, 12 is a common factor here. We can pull a 12 out on both of it. So that'd be 3, 4, 3, right? So therefore, we plug in here 2, 3 minus 2, that's the normal plane 1. And then the normal of 2, which you just found, was 3, 4, 3. So we substitute that in. So I have 3, 4. Minus 2 and 3. Minus j of 2 and 3. Minus 2 and 3. And then plus k of 2, 3. 2, 3. 3 and 4. Okay. Now we should get the right vector. So I of, let's compute the determinants here. So 3 times 3 is 9. 9 add 8, which should be 17. And then minus j of 6 add 6, which should be 12. And then plus k of hang on. Okay. Hang on, there's still something wrong here. So, hang on, what's going on here? I'm plugging the wrong numbers in. Let me have a look. That's why, because it's a negative I here. It's negative 36. Okay, it's my bloody negatives, man. Yes, so minus 6, minus 30. So it's minus 36, not plus. There we go. So it's minus 3 there. So that'd be minus 3 there. Minus 3. Minus j of 2, minus 3. And then k of minus 3. So then minus j then would be 6. 6 minus 6, which will go to 0. And then plus k of 8. 8 add 9, which should be 17. So then we get the vector d, which is 17, 0, 17, which simplifies again because it's a vector. We can put a multiple out, so we get the direction 1, 0, 1. Okay, and therefore we got there in the end. Just bloody write the one numbers down. I don't know why. I don't know what I'm doing. It's too late. Clearly, I'm really tired. I'm not gonna lie. We're nearly there though. R is, we know the point on there, which is minus 17 minus 7, and now we tack on the direction vector, which was k lots of 101. Okay, and that is the answer. Okay. Uh, okay. So that's and again I have a really sneaky feeling. Um, okay, so I found the line of the intersection. I have a really sneaky feeling. Let's go back to the paper. That they are going to ask you to find a vector equation of a line of intersection of 2 or 3 planes. And that's kind of the method behind that, usually, anyway. Um, so make sure you do. I've noticed this in previous years now. In recent years, there was a question. There are questions asking you to deal with line of intersections and finding the vector for it. So make sure you are comfortable with being able to do that. And so yeah, so that's the main goal with that is to use the cross product to find a vector that's perpendicular to 2 other vectors. That's the whole idea of that cross product, and it's in the formula book as well. So you don't need to remember it. It's up here. Hang on. There it is. The vector product A times B. That is the cross product. It's this little vector here, or alternatively, that's how it is, okay? But I prefer to do this is a 3 by 3 determinant. You should be able to deal with 3 by 3 determinants and matrices. So yeah, A times B. Those are 2 vectors. This will give a vector that's perpendicular to both A and B. Okay, so that's the whole goal of cross product. This will chuck out another vector that is perpendicular to A and B. Okay, so I really do think you don't even have to learn it really. It's giving you in the formula book. If you know determinants, which you should, I mean, there is. It's a really, really powerful tool in vectors to be able to find a perpendicular vector that's perpendicular to 2 other vectors, which, as we've seen, we needed to do it twice actually. So it really comes in handy, something to know. Anyway, so this final question before we leave it there, it says, given that we have 3 planes now, with the equation of this, the r dot 11a is equal to b, that's plane 3, and it tells us that the 3 planes form a sheaf. So what that means is, and then find A and B. So you should remember, again, in matrices, if 3 planes form a sheaf, that means they all intersect at a line, okay? So it's kind of like what's happening already, actually. So we are already given that pi 1 and pi 2 intersect in the line, right? Pi 1 and pi 2, they already intersect that in the line, which was L3, which we found in part D, okay? But it's telling us that pi 3 forms a sheaf, so pi 3 also intersects with the both planes in a line. Well, it's going to be the exact same line, isn't it? Because there's only one common line between pi 1 and pi 2. So that if pi 3 also share the line, it has to be this line, right? It has to be L3. So that means that L3 is also in pi 3. If since pi 1, pi 2, pi 3 form a sheaf. So they all intersect in the line, all 3 planes, which was L3. So I think because we know what L3 is now, the equation, we can just substitute some stuff in. But so L3, let's reiterate, was minus 7 to minus 7. Add k lots of 101 and pi 3, and that's equal to r by the way. And pi 3 is r dot, sorry, 11a is equal to b. That was in the question. Okay, so let's think about this. So we have again, I guess it's really, really useful to visualize this in your head. But this is pi 3, and L3 is contained in pi 3, right? As it's a line of intersection, so the whole line has to be pi 3. So we could substitute stuff in. Uh, um, well, I guess there's two ways of doing this, right? You could either substitute two different values of k, so say k0 and k1, um, and then you can form simultaneous equations, because then you could say, well, when k is 0, well then r is minus 7, 2 minus 7, and that's dotted with 1, 1, a equals b, and therefore that means minus 7 plus 2 minus 7, a has to equal b. Hang on, was that the equation, was it? 1, 1a? Yes, yes, okay. And then you could say, well, therefore, b is minus 7a minus 5. That's equation 1. Then you could say when k is 1, so k is 0, k is 1. Because if we know 2 points on L3, they will also be in pi 3 as well, because all of L3 is in pi 3. So that's what we're doing here. So R then would be minus 7 add 1, that would be minus 6. 2 add 0, minus 7 add 1, it would be minus 6. And that would be dotted with 1, 1a to equal b. And therefore, minus 6 add 2, minus 6a is equal to b. Therefore, b is minus 4 minus 6a. And there you got two equations, and then you can plug them perhaps in your calculator something. So minus 7 equals 5. Minus 6. So then if you solve them, solving 1 and 2 simultaneously, you get a is minus 1 and b is 2. Alternatively, that's like, I guess, a systematic way of doing it. Alternatively, well, since L3 is in the plane, we've already discussed this loads of times now here, but the normal vector to pi 3, which is actually 1, 1a, that has to be perpendicular to the direction of L3. So, alternatively, we could say 1, 1a dotted with the direction vector, which is 101, has to equal 0, right? Because the dot product of two perpendicular vectors is 0. That means 1 add 0 add a equals 0. Therefore, a is minus 1, which we've got here, okay? Minus 1. And then to find b, well, we know because pi 3 has the same line of intersection as pi 2 and pi 1, and we know minus 7 to minus 7 is in the line, then minus 7 to minus 7 will also be, as you can see here, right? The point, every point on L3 is on pi 3. So minus 7 to minus 7, as we've seen before, is on pi 3. So we can sub uh, R is -7 to -7 into R dot, well, 1, which is 1, minus 1 equals B. So therefore, that would get -7 plus 2 plus 7 equals B. And that would mean B equals 2. There we are. So there's two ways of doing that part. That last part of the question. Um, but yeah, so that's that then. Ah, oh man. Okay, hopefully that has helped. Okay, yeah, and these are the sort of predicted topics and even kind of predicted questions, really, that will come up in your paper too. So yeah, I've just gone through the major topics. We'll go through some more tomorrow, including this one, um, for practice for Thursday. But really, this stream should be really useful, though. These are the predicted topics, and I think these are the ones that are well, very, very likely to come up, if not guaranteed, right? Obviously, there might not be exact questions, but you will get very good practice by looking at this yourself, doing it yourself, and then reflecting with my answers and how I do things, how I go over it. Obviously, I made a few slip ups, mainly due to the fact I can't read, I'm writing down the wrong numbers and stuff. But yeah, hopefully my explanations will help. That's all it is, obviously. This is not meant to overtake your revision. It's just meant to be an extra resource, right? But hopefully this has helped. I am actually going to leave it there because it's quite late. But yeah, we'll do this. Do another similar stream tomorrow to go over some more predicted-ish questions. But any questions, let me know. I'll put this on my YouTube, and I will see you tomorrow if you're there. But I'm going to leave it there now. Okay.